Righty, I hope you are enjoying sunny Colorado. We have 300 days of sunshine here. So right now it looks more like Ireland or Denmark, where I'm from. This morning the theme is design of dynamical cores. And we're very honored here to have Professor Dave Randall from CSU here. He has been involved in DCMIP from the very beginning. He actually wrote the foreword to that book I showed the first day, and he's been working on dynamical core dynamics and also convection schemes, superparameterization, and so on. So we're looking forward to your talk.
Thank you, Peter. Okay, so I've been asked to talk about vertical coordinates, and then after the coffee break, I'm going to give a shorter talk on MPAS. So this is an outline of what I'll discuss, and not much point in reading it to you, but a fair amount of variety here. So the first thing to say is that, this is sort of obvious, but up and down are different from the horizontal coordinates because, first of all, gravity acts in the vertical, and it's very powerful, and gravitational potential energy is the source of atmospheric kinetic energy. And then we have a lower boundary that's pretty complicated, as you can see over there. Land and sea and mountains and vegetation and all that, and strongly influences things. And of course, that implies lower boundary conditions, which we'll talk about. Then going up, the density of the air decreases strongly, and so you have to deal with that in some way. And one issue that arises is upper boundary conditions, which I'll talk about briefly. Then a less obvious point is that the Earth's atmosphere is shallow compared to its horizontal extent. So the combined depths of the troposphere and stratosphere are order 1% of the radius of the Earth. So it's, atmosphere is shallow in that sense. So when we're considering large scales, like hundreds of kilometers or more, the horizontal derivatives are relatively small. The horizontal wind is relatively large. I say relatively, meaning compared to the vertical. So in large scales, vertical motion is slow, and vertical gradients are much larger than horizontal gradients. But if you get down to like cumulus scale, a few kilometers or less, then horizontal and vertical gradients are roughly the same size, can be locally anyway, and the vertical velocity can be comparable to the horizontal velocity. So if you're going to deal with strong vertical gradients, you need to find vertical grid. We'll talk a little bit about that. And if you have a fine vertical grid, then you're going to need short time steps to avoid computational instability. So for all these reasons, up and down are different from the horizontal. And a subject that's closely related to vertical coordinates is the choice of the equation set. So you're all familiar with the quasi-static approximation. Get this to move. I don't know how that turned on. I didn't do it. But quasi-static approximation, of course, is a change to the equations that describe what's going on with the vertical. In particular, it's a simplification of the equation of vertical motion. Then there are various anelastic approximations. Anelastic means sound filtering. Some of them filter only vertically propagating sound waves. Others filter all sound waves. There's the thin atmosphere approximation, which I'll come to on the next slide. It's customary to neglect the cosine latitude Coriolis terms, but there's a lot of reason to think that that may not be a good idea, especially with fine grids. Neglect of the centrifugal acceleration, you probably remember that from some dynamics class. Approximating the shape of the Earth as a sphere, and uniform gravity. We almost always do that, but we'll probably stop doing it at some point. So we're gradually eliminating these approximations, and the quasi-static approximation is the first one out the door. Not working. This thing has stopped functioning. Oh. Okay, thank you for that. Now we go back in. How do we do that? Full screen, view, full screen. Yeah, that one's fine. Okay, thank you. Okay, so I mentioned the shallow atmosphere approximation. If we don't make that approximation, then we have a deep atmosphere, and the important fact is that, as shown in this little sketch, if this point is the center of the Earth, and these lines that you see going out radially are lines of constant latitude and longitude, then as you move further away from the center of the Earth, they get further apart. And that shows up in the equations. So in the divergence operator, which is written out here in spherical coordinates, you've got an R square inside the DDR, and that's what that's doing. It's taking into account the spreading of the radius lines. And so if I use the product rule for differentiation to break this into two pieces like this, and if I neglect the second one, then the divergence is approximated this way, and that is part of the shallow atmospheric approximation. So most models use the shallow atmospheric approximation now, but that is slowly changing, and I'll say more about it in my next talk. Okay, vertical coordinates, which is the main subject today. Stairways to heaven, okay? Issues to consider. Long list here. The form of the lower boundary condition, so we'll talk a little bit about this, but obviously simpler is better. The form of the continuity equation. So, for example, it's simpler in pressure coordinates than it is in height coordinates. The form of the horizontal pressure gradient force can be either one term or two terms. Simpler is better. Pure gradient is particularly good. Form of the hydrostatic equation, even if you're not using the hydrostatic equation, the solution you get should be almost hydrostatic. So it still matters, and simpler is better there. The method used to compute the vertical motion, depending on what vertical coordinate you're using, this can be very different. We'll talk more about that. And the strength of the vertical motion as seen in the coordinate system. So in some coordinate systems, in a sense that I will explain later, there is no vertical motion. Okay, so here's just a few options. There are certainly more. But height, pressure, sigma, and sigma z. Sigma is a terrain following pressure coordinate, essentially, and sigma z is a terrain following height coordinate. Hybrid sigma pressure, which we'll talk about. Potential temperature theta, and a hybrid sigma theta. So all of these things are possible and more. So let's start with the continuous equations in height coordinates. And these are slightly simplified. I'm not worrying about moisture in this particular slide. And I really won't talk much about it at all today, just a little bit. So the first equation is continuity, right? W is the vertical velocity. W is the time rate of change of the height following a particle as it moves. The second equation is the horizontal equation of motion. My notation for horizontal wind vector is lowercase boldface v. Third equation is vertical velocity. So if I drop the left-hand side and I drop the friction terms over here on the right, I get the hydrostatic equation. And then this one down at the bottom is the potential temperature equation, where Q is the heating and delta is the dissipation rate. Dissipation of kinetic energy. pi is the Exner function. It's Cp times P over P naught to the kappa. So there are problems with this thing. It's very intuitive. You know, in ordinary life, we think about height normally, but height surfaces intersect the ground. So a surface of constant z will run into the hills over there. And so you need a boundary condition. And that can slow the code down in some ways, and it can also make the code more complicated. So nice to avoid that. If we don't use the, if we don't use the quasi-static approximation, then we simply predict W, as I showed you on the preceding slide. But if we do use the quasi-static approximation, then turns out the vertical motion is determined by something called Richardson's equation, which is this beast. So on the left-hand side, you've got dW dz, the rate of change of vertical velocity with height. And on the right-hand side, you've got horizontal advection of temperature and v dot del P and convergence of the horizontal wind vector and heating rate out here at the end. It's just a mess. And, you know, there are derivatives, and here's an integral. So this is nasty. And it can be integrated. I'll show you an example here on the next slide. The physical meaning of this and the way that you derive it is to assume that the vertical motion W is whatever it takes to maintain hydrostatic balance over time. So hydrostatics don't apply just at an instant, they apply continuously as things evolve. That's where this equation comes from. And this was used in the original NCAR GCM, which I will talk very briefly about in the next presentation. It used height coordinates and it used Richardson's equation. So here's an example just to make you believe it works. So if you drop all the terms involving horizontal motion, then it simplifies dramatically to this. So here's dW dz. On the right-hand side, I've got the heating rate Q and the time rate of change of the pressure at the top of the coordinate system. If W is 0, this will be a boundary condition at both the surface and the finite top height, Z top. Then the pressure at the model top changes according to this. So if I have heating, Q positive in the numerator here, that'll try to make the pressure increase with time. This is what happens when you put a pot of water on the stove, instant pot, right? So the pressure inside goes up with time as you heat it. Substituting back, you get this expression for the vertical velocity. And so it's at a height Z, and Z appears as the upper limit of this integral. So basically this says that W will be a positive number at height Z if I have heating in the domain. So if I heat, the air gradually expands, and that means it moves up past a given height surface. So now what we're going to do, and I'm not going to show you any details, but we're going to transform to an arbitrary vertical coordinate. And I have a typo. It's supposed to say denoted by Z hat. We assume that Z hat is a monotonic function of Z. That's the primary coordinate requirement for anything that you're going to use as a vertical coordinate. And we also assume that Z hat can be differentiated with respect to time and the horizontal coordinates. And the dimensions of Z hat, another typo, right there, that should be Z hat, can be different from those of Z. For example, Z hat might be pressure. And isosurfaces of Z hat are in general not parallel to isosurfaces of Z. They can be tilted with respect to each other. But the direction of the unit vector is perpendicular to isosurfaces of Z. In other words, it points up. We'll come back to that. So that, the way I would summarize that is up is up, no matter what vertical coordinate system you're using. If I'm using pressure coordinates, that doesn't mean that the unit vector pointing upward is perpendicular to the pressure surfaces. It's still perpendicular to the height surfaces. And in addition, The meaning of the horizontal wind vector is unchanged. It doesn't matter what coordinate system you're using, it's always the same thing. So, sketch of transforming from a coordinate z here, these are lines of constant z, the black ones, to a coordinate z hat, which is tilted, so this is a surface of constant z hat. And if I want to take the derivative of something called f, I can define points A, B, C in this diagram and write, df dx at constant z would be f at b minus f at a divided by x2 minus x1. That's what this says right here. And then I can play around with the equation and transform it to this form, and then take the limit as delta x and delta z go to 0, and I get the partial derivative with respect to x at constant z, that is along this black line. Sorry, I can't aim this thing very well. Along this black line is the partial derivative along the blue line. That's the second term here. And then there's a correction proportional to both df dz and dz dx at constant z hat, which is basically the slope of the blue line with respect to the black line. So from this, you can get this formula for the gradient at constant z, the gradient at constant z hat, and also the divergence of a vector like this. So using algebraic machinery like this, you can derive a system of equations. I'm going to start from this system, make that kind of transformation, and we arrive at this system, okay? And it actually looks almost the same. So for example, the continuity equation, pretty nearly the same. I've got a time derivative of something called rho sub z hat, which I'll define in a second, at constant z hat, but this looks like d rho dt. I've got a del dot at constant z hat, rho hat again, rho z hat again times v. That looks like del dot rho v. And then here's the vertical derivative, it's d dz hat, and I've got rho sub z hat again times w hat. So we have to define rho sub z hat, that is called the pseudodensity, and it's the ordinary density rho here times dz dz hat. So you can see rho times dz is the same as rho sub z hat times dz hat. It's the amount of mass per unit horizontal area between two isosurfaces of the coordinate. W hat, which appears here, is this. So it involves the time rate of change of z at constant z hat, and there's a kind of horizontal advection term, v dot del z at constant z hat, and then w, the ordinary vertical velocity. So w and w hat are closely related. If z is z hat, which is of course one of the possibilities, then this ratio, this derivative is just 1. This time change will be 0. This horizontal gradient of z would be 0, and you just get w hat equal w. Okay? When we write the Lagrangian time derivative, the capital D dt, we use w hat. Okay, so that's implicitly here and here and here. Okay? The pressure gradient force in the horizontal equation of motion has 2 terms now. There's a derivative of the pressure at constant z hat, a gradient pressure at constant z hat, and then a correction term that's proportional to the gradient of z on a z hat surface, and proportional also to, dp dz. The vertical equation of motion is just 1 over rho sub z hat, the pseudodensity, times dp dz hat. So that, that looks almost the same. Just get rid of the hats. And then I've got minus g. So if I was to make the hydrostatic approximation here, I would drop the left-hand side, and I would drop the friction term over here on the right-hand side, and I would just get these 2 terms balancing each other, and it looks almost like hydrostatics in high coordinates. So that's how it comes out after several pages of algebra. Okay. And I did not make the hydrostatic approximation here, as you can see. So what are we going to do with W hat? So we already looked at this equation. I copied it here. This is the definition of W hat, and there are two ways to use it. One way is to specify a formula for W hat somehow. I'll give you an example in a minute. So if I do that, then I know the left-hand side, and I can use this equation to get the time rate of change of Z on a Z hat surface. That's one possibility. So examples of this first approach are listed down here. First of all, if Z hat and Z are the same thing, then as I told you before, W hat and W are the same, and the equation of vertical motion is how we determine W, of course. And so this equation would just reduce to dz dt equals 0, which of course is the right answer if Z and Z hat are the same thing. That should be a Z hat subscript, I just noticed. Lots of typos here. Okay, second possibility, if Z hat is potential temperature, theta, then W hat is theta dot, which means the time rate of change of theta following a particle, capital D dt of theta. And that, of course, is the heating rate, basically, and that's parameterized. So in this case, W hat would be determined by the physical parameterizations of the model. So again, I would know the left-hand side, and I could use this equation to calculate the time rate of change of the height of a constant theta surface in this case. Okay? Now, the second way to use the W hat equation, which is copied again at the top here, is something called ALE, arbitrary Lagrangian or Eulerian method. So the name comes from this. It's arbitrary, first of all, in the sense that any physically useful rule can be used to determine dz dt at constant Z hat. So the idea is we're going to specify this somehow and use this equation to calculate W hat. Okay? So it's kind of the opposite of what we did in the first approach. The method can be Lagrangian if we basically use this formula to track surfaces as they're advected. I'll show that on the next slide. And it can also be Eulerian because if I set dz dt constant Z hat to 0, then Z is a fixed Eulerian function of Z hat. So examples, if Z hat is simply, Z equals Z hat is simply advected by the wind. So here's the surface and the wind's blowing and it just gets carried along and no mass crosses it. Okay? Then this equation would reduce to that. And this is how you would predict where the coordinate surface is in the sense of what is its height. Okay? So this is the Lagrangian approach. And the reason this might be interesting is that if the coordinate surface is just advected, that means, and no mass crosses it, then you don't have any mass entering or leaving model layers across the layer edges. And that is useful in many ways, one of which I'll show you in a little bit. Second possibility, we could use something like this equation, but modify it so that the advected surfaces don't run into the lower boundary or the upper boundary, and they don't get too close together and they don't get too far apart. Those are all useful, practical things. So in that case, we'd be trying to let the surface be advected with the wind, but we have some safeguards so that nothing bad happens. ALE is used in various places, including in ocean models. Okay, boundary conditions on the continuity equation. So what I'm doing here on the top is I'm integrating the continuity equation in Z hat coordinates through the column of air all the way from the surface to the top of the model, Z hat T. And I took the integral inside the derivative. So here the integral is inside the time derivative. Here it's inside the del dot, okay? And when you do that, you get some correction terms because the limits of integration might be changing with time or they might be changing in the horizontal. So those correction terms are grouped over here. And I've also included the vertical velocity terms here. So what you see is this same kind of expression that we just talked about, except this time we've got a hat on the z. And so what these terms represent mass fluxes across the top of the model, which should be 0, right? And across the Earth's surface, which should also be 0. So if we want to impose those two boundary conditions, we have to put them in. We simply drop these two terms. And that'll give us what amounts to the surface pressure tendency equation if we were to assume hydrostatics. So speaking of hydrostatics, most models still use it. Most global models still use it. What happens? Well, first of all, as you know, the equation of vertical motion can no longer be used to predict W, but we have to get W somehow, and I already showed you that we use Richardson's equation in the case of height coordinates. Secondly, if we have a fully compressible model, there's another typo, we must prognose, not prognosis, two thermodynamic variables, like, for example, the density and the potential temperature. But if you use the hydrostatic equation, then if you predict, let's say, just theta, you can get the density and the pressure from two equations, the hydrostatic equation and the equation of state. So with the hydrostatic approximation, you can only predict one thermodynamic variable. There isn't room to predict more than one. And the other important thing about the quasi-static approximation is that it filters vertically propagating sound waves, which we'll come back to. The quasi-static approximation is not the same as the hydrostatic approximation. Most of you probably know this. So this is a statement of hydrostatics. But when we use the quasi-static approximation, we determine the pressure by vertical integration of that and use that pressure to calculate the horizontal pressure gradient force. So this approximation by itself is almost always justified. There's an error, but it's very small, even in a thunderstorm. But this approximation is more difficult to justify, especially when the scale of motion is small and the vertical velocity is strong. There is a trend to non-hydrostatic models, as you all know, partly associated with the increasing speed of computers. And the work with these global non-hydrostatic models is taking advantage of all the research that's been done by mesoscale numerical modelers over the last several decades. So a lot of the things that they learned are directly applicable to the global models. Pressure coordinates, just briefly, I mean, you're all familiar with this, but the continuity equation looks like this. So you can get the vertical velocity omega by integrating that with the boundary condition. But the lower boundary condition is complicated. It looks like this. Time rate of change of the surface pressure and Vs dot del Ps and omega S. Pressure surfaces intersect the ground just like height surfaces. But pressure surfaces intersect the ground at places that change, different places on different days. And so it's worse. And as far as I know, the only global model that's ever used pressure as a vertical coordinate was Chuck Lee's model at Livermore, which existed for a couple of years back in the 1960s. Now, as a comment, hydrostatically, the pressure at a given level is the weight of the air above, and that includes the weight of the water. So you have water vapor, and you have condensed water, and they all tend to increase the pressure at a given height below them. And of course, the distribution of water can change due to what the parameterizations are doing, right? You can have cumulus updrafts transporting moisture. You could have condensation and precipitation going on. So that's complicated. And it's really good to avoid those complications. I think there's fairly uniform agreement now that the best approach is to use the dry hydrostatic pressure, which is just what it sounds like. It's the weight of the dry air above a given level. And this is what CAMSE does, I believe. Also, in a non-hydrostatic model, which has sound waves, the literally noisy pressure field, I omitted the word, pressure there, is not an attractive candidate. You don't want to have your vertical coordinate system vibrating on you, okay? So what you can do is define a hydrostatic pressure, even though you're not actually using the quasi-static system. You can still define a hydrostatic pressure. For example, if you know theta at every level, you can do some algebra and use the hydrostatic equation and the equation of state and get a formula for the pressure. So it's not the actual pressure because it's a non-hydrostatic model, but it's hydrostatic pressure. And so the best way to go, in my opinion, is to use the dry hydrostatic pressure in that sense. And that can be used to build, for example, a sigma coordinate, which we're going to talk about. So here we go, terrain following coordinates. You all probably are aware of this. So the gray shading at the bottom here is supposed to represent topography. And these are coordinate surfaces, these sort of bluish purple lines. And they follow the topography near the lower boundary. They gradually get smoother as you go up toward the top of the model, but only gradually. And the advantage of this approach is that, well, first of all, this is one way to define sigma. So you take the pressure at the top, or the dry hydrostatic pressure at the top, which would be the same thing actually, and the dry hydrostatic pressure at the surface, and use them here to calculate sigma as a function of P, as a function of dry hydrostatic P. And this formula says that if P is equal to P top, like up here, then sigma at the top is 0. And if P is equal to PS, like down here, then sigma is equal to 1. So that's nice. It's also possible to define a sigma z, same kind of idea, except you use height instead of pressure. So major advantage of this approach is that the lower boundary condition just becomes sigma dot. That's the Lagrangian time rate of change of sigma following a particle. Sigma dot equals 0 at the bottom. That's nice. And sigma dot equals 0 at the top. So the upper and lower boundary conditions become very, very simple. And that's a tremendous advantage of terrain following coordinates. So if you want to calculate vertical motion, I'll illustrate that for the case of sigma coordinates. In this case, the pseudodensity, using the formula I showed you before, would be minus pi over g, where pi is a shorthand notation for ps minus p top. P top's typically a constant, so changes in pi are just due to changes in the surface pressure. The continuity equation in sigma coordinates becomes this. The nice thing here is that the thing under the time derivative is not a function of height. It's one number for the whole column because it's ps minus p top. So this is relatively simple in that way. If I vertically integrate this through the column and use the upper boundary condition and the lower boundary condition that sigma dot is 0, then I get this, which is, again, remember, pi is ps minus p top, so d pi dt is basically dps dt. And then this is the divergence of pi v d sigma. Well, pi d sigma is dp. So it's the divergence of v dp, basically. And so this is the surface pressure tendency equation in a somewhat unfamiliar looking form. The integrals from the surface to the top, or top of the surface. So I get this from here by integration. So the way the model works is you write a do loop to integrate this as using the known horizontal wind. And when you integrate through the whole column, this term drops out because sigma dot's 0 at the top and bottom anyway. So you just get this. Now I can calculate d pi dt, and then I can go back. This is known. So I can calculate sigma dot by integrating this again. So you have one vertical do loop to get the surface pressure tendency, and a second vertical do loop to get sigma dot by integration of this, basically. That's pretty simple. But there's a problem with terrain following coordinates. And that is that the horizontal pressure gradient force has two terms. So in the case of sigma coordinates, these, one term is proportional to the gradient of the surface pressure, and the other term is proportional to the gradient of the geopotential height on a sigma surface. So here's a cartoon mountain, this thick line. And on this side of the mountain, where the mountain is sloping up to the right as you go to larger x, the surface geopotential is increasing with x, and of course the geopotential of the sigma surfaces are also increasing with x here because they're following the terrain, but the surface pressure is decreasing with x. So that means these two terms here are of opposite sign. Now, nothing wrong with that in principle, but suppose that these two terms are both very big because the mountain is really steep, okay? Like the Flatirons out there. Well, then what we really want is the sum of these two, and the sum of these two, if the mountain is steep, is going to be very small. This is going to be very small compared to the individual terms on the right-hand side. So if I have, let's say, a 1% error in each of these two terms due to numerical approximations, well, that may be about the same size as the thing I'm after on the left-hand side, in which case the error totally destroys the information in HPGF. So the nasty thing about this problem is that it gets worse as you increase the horizontal resolution. You like to think if you increase the horizontal resolution, everything gets better. But this gets worse. And the reason is that with higher horizontal resolution, the mountains get steeper on the grid. So the individual terms on the right-hand side up here get bigger. And again, they have opposite signs. So that's unfortunate. So that has motivated the creation of hybrid sigma pressure coordinates. And I just have one sketchy slide on this, but this is very widely used. The most famous paper on this subject is by Simmons and Burridge up here, 1981, a long time ago. So they invented a combination of sigma and pressure coordinates, which I'm calling sigma sub p. Okay? And it involves the pressure itself, like right there, and also right there. It also involves PS, which you see here and here and here. And it involves P top, okay, top of the model pressure. And it involves one more thing, something called P sub 0. Now, this is not the P sub 0 that you use in the definition of theta. This is separate thing, and you choose it when you set up your coordinate. It's a positive constant. It has units of pressure, of course. And Simmons and Burridge showed that sigma p is monotonic with pressure, which is, of course, necessary, provided that P naught is bigger than PS over 2. Okay? So provided that this inequality is satisfied, you can choose P naught to suit your application. When you do this, sigma p turns out to be 0 at the top of the model and 1 at the surface, just like sigma. So that's convenient. It's still terrain following, And you still have a simple lower boundary condition and a simple top boundary condition. And it works pretty well for surface pressure variations in the range 1,000 hectopascals to 500. So you still have two terms in the pressure gradient force, which I'm not showing here, but one of them is strongly dominant, at least once you get a little ways up away from the topography. So a quick comment on the vertically integrated horizontal pressure gradient force. That's a mouthful, so I abbreviated it here. What I've written here is actually the three-dimensional pressure gradient, del P, and I'm integrating it with respect to height from the surface to the top. And I'm not assuming anything about constant z dop or anything. Then what I do is I take this integral inside the gradient operator like that, and I have to pick up terms that represent possible variations of zs and zt in the horizontal. And now let's integrate this around a closed path. So you can draw a line on the Earth like on a topo map, okay? Around a closed path, but it could be, to keep it simple, it could be a latitude circle, okay? And so when we do that, we get this, but wait a minute, where's the line integral of the first term? Well, it drops out because the first term is a gradient. The line integral of a gradient around a closed path is 0. So you just get these two terms. And so the first one, involving the surface pressure and the surface elevation, represents a force felt by the atmosphere when the pressure is high on one side of a mountain and low on the other side. So it's form drag on the mountain. It's what's called mountain torque in the context of the global circulation. The second term is the same kind of thing, but at the top. You don't want mountain torque at the top, okay? So we want this term to be 0, and that'll be true if p top is a constant, because in that case I can pull it out of the integral and I have the line integral of a gradient, that's 0. The other possibility is that z top is a constant, in which case it's gradient 0. So if either p top or z top is 0, this will drop out. And that's what we need to do. So let's see how that would work with vertical differencing, okay? And I'm going to do it for the case of sigma coordinates, but this can be done with other coordinates too. So here's pi times the horizontal pressure gradient force. Remember, pi is ps minus p top. And it can be written this way after a little bit of algebra, which I'm not showing you. So these are the two terms of the horizontal pressure gradient force, but after some manipulation. So the first one involves dd sigma of sigma phi times a gradient, okay? Gradient of the surface pressure. And then the second one is, again, a gradient of just pi theta. Well, vertically integrating, well, in a finite difference model, what you would do is approximate this vertical derivative this way, where here delta means the difference between neighboring model layers. And then to do the vertical integral in a finite difference model, what you do is multiply by the delta sigma for each layer and then sum instead of integrating. And so what you get is this del pi and this second term. This sums to phi sub s. The sum right here. You're adding up all the delta sigmas times phi, and you end up getting phi sub s. And it multiplies del pi. Now if I take an integral around a closed path in the horizontal, this will drop out, or sorry, this will drop out because it's a gradient. And this gives you the mountain torque. This is the form drag on the topography down here. So that motivates using the pressure gradient force in a form like this, which is not something that you would come up with if you didn't have a reason to look for it. Okay, now speaking of boundary conditions, we have, of course, vertically propagating waves of many different kinds. So a lot of the time we have vertically propagating gravity waves over the mountains west of here. And when those waves get to the top of a model, if you just have a lid boundary condition where the vertical velocity is forced to be zero, then the waves could be reflected. And that means they come back down. And of course, that doesn't happen in the real world. So this is bad. So if you just consider one particular type of wave, like gravity waves, for example, gravity waves, then you could try to formulate a radiation condition. This has actually been done by Joe Clem. But we have lots of different types of waves. And formulating a boundary condition that will let them all out, a radiation condition for all types of waves, is, I think, a hopeless problem. So what we do instead is damp the waves out near the model top, not just at the top, but in the top few layers. And that's done by including usually a Laplacian, a friction term, in the momentum equation. And the details are rather arbitrary because, of course, nature doesn't do this. But this approach can prevent spurious downward moving waves that reflected off the top. If the top is higher than about 100 kilometers, I'm not quite sure of this number, but pretty high, then the molecular viscosity is large up there because the molecular density is small. And so it acts like a true physical sponge. Another typo here, a sponge, a true physical sponge. And that means that you wouldn't need an artificial sponge layer in such a case. But of course, most models don't have their tops that high. So I'm going to talk a little bit about theta coordinates. And the first thing to say is that there have been many people, these are all pictures of men, I apologize, but it's just what happened. So lots of different prominent scientists who have been advocates of the theta coordinate. It's not very widely used for reasons that I'll mention. But what are they like? Well, first of all, there's no vertical motion in the absence of heating. The rate of the vertical motion in theta coordinates is theta dot, as I told you before, and that's proportional to the parameterized heating. Well, through most of the atmosphere, most of the time, the heating rate is fairly small. So that means the vertical motion is pretty small, and it means that the theta surfaces are almost just affected by the wind. So that's nice because it means no mass crosses them, and the mass in a layer just moves around inside the layer. That would also happen with ale, of course, or could, depending on how you do it. Another nice thing about theta coordinates is that the pressure gradient force is a gradient, and that can be used, for example, to derive a potential vorticity equation, which I don't have time to talk about here. Wave momentum transport occurs via isentropic form drag. This means form drag on isentropic surfaces. I don't have time to explain this here, but it's very nice. It means that momentum exchange between neighboring layers is mostly just due to the layers pushing on each other. It's easy to implement diffusion along theta surfaces. We expect diffusion to act mostly along theta surfaces because diffusion itself is an isentropic process. And it's straightforward, well, relatively straightforward to conserve both energy and entropy with this system. Again, I don't have time to talk about that. And it can help with places where the potential temperature surfaces get very close together. For example, at the top of the boundary layer, the temperature, the ordinary temperature, often increases upward, like above the clouds today outside. And that means potential temperature, of course, also increases upward, but very rapidly. So the theta surfaces are very close together. And if you use theta coordinates with suitable numerics, this can be a good thing. Now, an issue with theta coordinates is that they intersect the ground. And of course, they intersect the ground in different places on different days, just like pressure. But Lorenz, who will come up again here in a minute, suggested that we could take care of that problem by defining massless layers. When a theta surface comes down and touches the ground like there, we just imagine that it continues along the ground and then maybe lifts off in the opposite hemisphere. So if you have multiple theta surfaces down on the ground, they're touching each other like coats of paint on top of each other. That means there's no mass in between them. But there's nothing wrong with that. It's physically okay as long as your numerics can handle it. But notice that in the tropics, because the surface potential temperature is pretty warm, there would be lots of theta surfaces on the ground. That means the layers you allocate to deal with the high latitudes are sort of wasted in the tropics. So that's unfortunate. So people have defined hybrid coordinates. So this is a cartoon sigma coordinate, which you already saw. This is a cartoon theta coordinate. These are the theta surfaces sloping down towards the tropics. And then this is a hybrid. So it looks like sigma near the ground, but it looks like theta up here, okay? And I'm not going to show you how this is done, but it's actually relatively simple. And it can lead to some nice results. So here's an example. This is due to Cello Conor. So this is latitude, North Pole on the left side. It's July, so this is the winter hemisphere over here in the summer hemisphere. And what's being plotted here is the log of the water vapor mixing ratio. And it's actually a difference between a simulation with a hybrid coordinate, like what I just described, hybrid sigma theta, and a simulation with plain sigma coordinates. And what you see, if you look at the color bar, is that in the stratosphere, there's less water, and in the troposphere, there's more water. So what the hybrid coordinate has done relative to the sigma coordinate is it's prevented moisture from being artificially diffused from the troposphere up into the stratosphere. And this is a step toward improved realism. Too much water vapor in the stratosphere can cause problems. So Christiane asked me to talk about the fact that vertical grid spacing generally changes with height. This is a depiction of 3 versions of the upcoming CESM, or CAM, I should say. So this is a low top model with the top at about 40 kilometers, a mid top model with the top at about 80 kilometers, and a high top model with the top up at 130 something kilometers. And so what you can see is that in all cases down near the lower boundary, the layers are relatively closely spaced. The dots overlap. You can't even see the separation. But as you go up, they get further apart. And that's what's typically done on these models. Thinner layers near the lower boundary, so we can handle the boundary there. Vertical staggering. I've got 9 minutes, so I have to wind this up. But when we define a vertical grid, we have to say where the variables of the model live. Where are they defined? And there are 2 ways to do this. One is called the Charney-Phillips grid, which was developed during the 1950s for use in quasi-geostrophic models. And the other one is called the Lorenz grid, which was essentially developed by Ed Lorenz around 1960. And most models today use the Lorenz grid. Most global models and most linear area models use the Lorenz grid. So the way this works is that the solid lines here are layer edges, and the dashed lines are in the middle of the layer. And in all cases, the winds are defined the horizontal winds are defined at the dashed lines in every case. So with the Lorenz grid, the potential temperature is defined to the same place with the winds. And that's convenient, of course, for reflecting theta. It's also convenient for tracking thermodynamic energy. With the Charney-Phillips grid, the potential temperatures are at the layer edges. So the wind is at the dashed line, and the potential temperature is at the solid lines. Now, why would you do this? Well, if we're on the Lorenz grid on the right-hand side here, then if I want to calculate the thickness between 2 dashed lines where I'm predicting the winds, then I need to know the geopotential, right? So I need a thickness. I'd like to have the potential temperature there, but I don't. It's here. So what I have to do is average it from the dashed lines to the solid line, and that gives me my thickness. Well, the problem with that is that, so this is the thickness between L and L plus 1 in terms of the average of theta at L and L plus 1. The problem with that is that if the potential temperature has a zigzag in it, so it's increasing upward but not smoothly, it's got a little zigzag, then the averaging makes that invisible. And if the model can't see the zigzag, it can't get rid of it. So you tend to get zigzaggy structure in the potential temperature in the vertical with the Lorentz grid. That doesn't happen here because the potential temperature is right where you want it to be to calculate the thickness. However, it's more difficult to do energy conservation with the Charney-Phillips grid. And so that's made it, that's made people reluctant to go in this direction. The UK Met Office started doing this a long time ago, 20 years maybe. And the Canadians are using the Charney-Phillips grid. And we'll see whether it spreads further. Okay, vertically propagating sound waves. I don't really have time to talk about this. I'm going to say a little bit about it in my second talk, so I'll skip this. Energy conserving vertical differencing. I have like 2 or 3 slides left. I'm almost done. So this is Ed Lorenz. I don't know when this picture was taken, but I'm guessing maybe around 1960. And this paper was published in 1960. So in this paper, he proposed doing vertical differencing in such a way that total energy could be conserved in a way that I'm going to explain on the next slide. So he was the first person to point to this as a desirable thing to do. And so the basic issue is this. You have a momentum equation, so it's predicting V. The kinetic energy per unit mass is 1/2 V squared, okay? So the momentum equation implies the kinetic energy equation. Even though you're not actually predicting the kinetic energy, it implies a kinetic energy equation. The thermodynamic equation implies an available potential energy equation. And as you know from dynamics, the way the atmosphere works is, to a large extent, the available potential energy is converted into kinetic energy. That's a big part of what's going on out there. So in the continuous system, the sum of the kinetic and available potential energies does not change under adiabatic frictionless processes. So the rate at which kinetic energy is being generated is exactly equal to the rate at which APE is being lost. What we'd like to do, and what Lorenz advocated, was design the model's vertical differencing scheme so that the same constraint applies in the model. And so the rate of conversion of available potential energy into kinetic energy is proportional to omega alpha, where omega is the vertical velocity and pressure coordinates, and alpha is 1 over the density. It's called the specific volume. So you can derive in the finite the vertically finite difference system, by starting from the momentum equation, you can derive this formula for omega alpha, and it's got a bunch of terms. And then by starting from the thermodynamic equation, you can derive this equation for omega alpha. It's got a bunch of terms. And what we want is for these two expressions to be equal to each other. So look at them. I've got this here, and again, right here. So this term and this term would agree if this coefficient agrees with that coefficient. Similarly, over here, I've got a pi sigma dot and another one there, each multiplied by a geopotential difference. Down here, I've got 2 pi sigma dots, each multiplied by some combination of t and theta. Okay, so I can make this term agree with this one by making this number agree with that one, and this number agree with that one. And that's a constraint on the hydrostatic equation. So this can be done, okay? And it sort of tells you how to do the hydrostatic equation, which is a good thing, because we need to do it anyway, and this tells us how. Okay, so conclusions. There are lots of vertical coordinate systems. I don't need to read this to you. So I'll just stop and let you read it. Thank you very much.
So the big Richardson equation, if you need to keep terms in that Richardson equation, simplify it, does the transformation to an arbitrary altitude grid still work?
If you simplify it by dropping some terms, then that means that the hydrostatic equation doesn't change in a smooth way as you take time steps. And that would introduce issues. You wouldn't want to do that.
So how did you solve it in the original GCM at NCAR?
Well, I don't remember the details, or you can read about it in that 1967 paper. But, you know, they need the heating rate. They need to compute the advection of theta and all the other stuff that you see there. And then that gives you dW dz, and you do an integral. That's how it works. So it's pretty complicated. And again, I don't remember the details, but it's in the paper.
MLFS?
The theta coordinates do seem really cool. I'm scared about the fact that they're not monotonic with height necessarily. But I was wondering if anyone had ever tried like using a wet equivalent potential temperature as the coordinate to try to capture some of the moisture.
Theta E is not monotonic. I mean, in the tropics, it typically decreases upward in the lower troposphere and increases upward above. So you can't really use that as a model coordinate. There are ways of using it in diagnostics. Olivier Pallouy has done that. It's useful, but I don't think it's suitable as a model coordinate unless you make a hybrid. So you could hybridize it with sigma.
The dry hydrostatic assumption still the case for models like CESM? I was wondering because if you put, like to simulate the Hunga volcanic eruption, people put like 100 teragram water vapor into single grid box because it didn't have the plume model. And I was wondering whether it makes the simulate the air mass lighter than it should be.
Yeah, well, there is that effect, and using the dry hydrostatic pressure as the vertical coordinate does not prevent you from including that effect in the model. It's just a coordinate system. So you can still include the buoyancy effects, the Dayang ideas with that. There's a question in the back.
Yeah, I mean, maybe I just misunderstood a little bit, but I was with the last thing with the Lorentz 1960, is that connected to the Lorentz grid? Or is that just how you get the right
Yes.
hydrostatic equation?
It's
or
connected
is
with the Lorentz grid in the sense that he used the Lorentz grid in that paper.
Okay, so is
And
this
what
also
he
why?
if you try to do what he did in that paper with the Charney-Phillips grid, you run into problems.
Where? Okay, why don't you go first and then we'll...
Okay. Kind of following up on our previous question, is there a way of dealing with convective instabilities in a dry isotropic coordinate model, or do you just kind of have to hope for the best?
The model can't see a convective instability. It isn't quite the right word, but it sort of filters it. It can't simulate it. So you could imagine that it's a kind of numerical parameterization of dry convective instability.
Do you mind while you answer, pull up the next presentation?
Yeah.
I was going to ask you your preferred vertical coordinate and your preferred vertical staggering, like if you could choose.
Well, I like Charney-Phillips, but I've never actually built a model with Charney-Phillips. So I say that without having experience with it. And in terms of preferred vertical coordinate, I think hybrid sigma theta is a very good choice.
Thank you.
Tops are at the bottom.
Oh, okay, thank you. Too easy for us.
That's to the left. There.
Mic is off.
Okay, what you'll need
Oh,
for the,
yeah,
for the next
we have a
one.
coffee break, right?
No,
Oh, we We don't, okay.
So you're on for
Well,
another
there we
half.
go. All right. So, the first question we're open is
Is that the one? Okay, thank you.
Oh, that's not big enough. Full screen. Doesn't look like full screen to me.
I have to like zoom in on each
Yeah,
slide.
well, I think I'll be able to read them. I must have made a mistake when I created the PDF. I don't know how that happened. But,
Maybe you can zoom and slide mode.
yeah, how are you using it?
And we come. Yeah.
I think you'll be able to see them. If you're sitting
Okay.
back, I apologize. I won't go into full screen mode. I'll stay this way so I can grab it and stretch it.
Okay.
At least I think I can. Nope.
Yeah, you can sign there to zoom in. Then we have to move it, yeah.
When I created this talk, I was under the mistaken impression that it was going to be a 50-minute talk like the last one. And I discovered last night or yesterday afternoon that it's only a 30-minute talk. So I stripped it down. I cut it in half, basically. It's been slashed and maybe a little bumpy because of that. So the MPAS Atmosphere Dynamical Core was created by Bill Skamrock, who you see on the left there, and Joe Klump on the right. And Bill gave me numerous slides that I've sort of adapted here. So the first thing I want to talk about, it stayed zoomed, is where MPAS came from. And as I think most of you know, it has a mesoscale heritage. I'm tracing it back here in a somewhat loose way, but the Klemp-Wilhelmsen model was created during the 1980s, if I remember right. And that is, in a sense, a precursor because that's where the idea of time splitting for the sound waves was first introduced. And I'll talk about that in a few minutes. It's a way of maintaining computational instability or stability. Then there was MM5, which was a very widely used mesoscale model. And then, of course, WRF, which is still very widely used. And then MPAS. And MPAS, well, there is a global WRF, but leaving that aside, MPAS is the first truly global dynamical core, and there is a regional or limited area version of MPAS, but I'm not going to talk about that here, but it's available. Because these models were developed essentially in the weather community and are now being used in the climate community, at least sometimes, they sort of bridge the gap between weather and climate. So this is the paper that was published in 2012, and I encourage you to look it up. I will explain what centroidal Voronoi tessellations are, and I will explain what C-grid staggering is. I would not have chosen this title. Okay, first thing to say is MPAS is only the second global atmospheric dynamical core that's been fully developed in-house at NCAR. The first one was the Washington Kasahara model. That was 1967, as I've already told you. 45 years difference there, okay? Discretization philosophy, just in very broad terms, it's a finite volume model, okay? And that term may be unfamiliar to you. So the idea is that in differential space, we can define operators like the divergence and the curl and the gradient as the limit of surface integrals over a volume of the vector quantity in question in these two, or the scalar A in this case, combined with an outward normal vector on the boundary of the, an outward normal unit vector on the boundary of the volume. And then you take the limit as the volume and the surface shrink to zero, okay? That's the definition of these operators. And the nice thing about these definitions is that they don't make use of any coordinate system. So here's a control volume which looks like a potato. And this is a little patch of area on the side. So that's, well, here I wrote ds, but this is labeled as d sigma. And there's an outward normal here. That's what I'm calling n here. So these definitions for the differential operators suggest finite difference approaches. So what you can do is replace the control volume by a grid cell. And instead of integrating over the surface of the control volume, you sum over the sides of the grid cell, okay? And that's how the finite volume method works. So here's an example for the simple case of mass conservation, okay? So here's the continuous coordinate system, continuous continuity equation. And so it has a time rate of change on the left-hand side and a minus del dot on the right-hand side. In the discrete system, this is discrete in time as well as space. I have the difference between two time levels, n and n plus 1. And here's the delta t over here. So if you divide by delta t, this is the approximation of the time rate of change. And then this sum for the time rate of change of rho and grid cell number j is a sum of the fluxes between into j or out of j from the neighboring cells, which are labeled j prime. Okay, so that's the setup. So this boldface f sub, not boldface, f sub j prime comma j is the flux from neighboring grid cell j into or out of, sorry, neighboring grid cell j prime into or out of grid cell j. So it corresponds to this flux here. And so in the continuous system, if I integrate the divergence operator over a closed domain, I get 0, okay? You can do that in the finite volume method by summing over j. I take this expression right here, which repeated here, and I sum it over j. I'm summing over the whole domain, and I require that I get 0. So my finite difference, my finite volume, del dot v, obeys the same identity as the continuous case. And of course, the time rate of change term, because of this, when I integrate both sides of this equation, if I use this on the right-hand side, I'll get the time rate of change of the integral over the whole domain of the density. And what the continuity equation will tell me is that doesn't change. The amount of mass in the domain doesn't change because all it's doing is moving between boxes. It's still in there. And that would follow from this and this, okay? You would conclude that the total mass in the domain at the end of the time step is the same as the total mass in the domain at the beginning of the time step. So that's the basic idea of the finite volume method. You can use a similar approach with the pressure gradient force, which I won't talk about here, and even to define a vorticity. Why is that there? Okay, so I'm scrolling down. Okay, vertical coordinate. One slide or two slides on this. So MPAS uses a height-based terrain following vertical coordinate, but it's not very similar to sigma. The definition is actually following a different philosophy. So the coordinate here is called zeta. And this equation relates the height of a zeta surface, z, I could write z of zeta here, to zeta itself, and the height of the terrain, which is called h. But this is h sub s, and the subscript s means smoothed, okay? But it's smoothed in such a way that if you put zeta equals 0 here, then you actually get the surface terrain. In other words, it's not smoothed at the lower boundary, but as you go up through the column, it's smoothed in a way that I'll tell you in a minute. So just to get a handle on this equation, what does it mean? Well, if there's no topography, then this term is 0, and you just get z equals zeta, okay? So it reduces the height coordinate if there's no topography. Not a normalized height. So in that way, it's different from sigma. It's just height. The smooth terrain height is created by smoothing using an iterative diffusion operator, which I'm not showing you, but you're essentially diffusing H horizontally at levels above the surface. And this is done outside the model, not while the model runs, outside the model as you set up the grid. So you create less smoothing, no smoothing at all at the lower boundary, relatively little smoothing near the lower boundary, and strong smoothing up here, okay? And then the other thing is you have something called A, which is also a function of zeta, and Joe Klemp calls it the hybrid attenuation profile. And it controls the rate at which the coordinate surfaces transition from terrain following at the surface to constant height aloft. So it's a kind of second smoother. And he says that he did this for flexibility. MPAS uses A equal 1 at the lower boundary and A equals 0 above some specified height, okay? And I'm going to refer to Klemp's paper, which is listed here for the rest of the details. So it's a different way to make a terrain following coordinate system using height as the base variable. What about the equation set? Okay, well, first of all, MPAS uses the fully compressible system, which means there are sound waves. And the justification for not filtering the sound waves is that filters introduce errors. Now, there are different ways to filter, and some of them have bigger errors than others. But at any rate, they chose not to filter because they wanted to avoid the errors. So, okay, reasonable. The equation set itself is shown here. I'm not going to talk about details, but these are the time rate of change of the horizontal wind vector. His notation is different from mine. This is the capital boldface V with the subscript H. This is the vertical velocity. This is potential temperature, including the effects of moisture, essentially virtual potential temperature. And this is a modified density. It's density divided by zeta sub z. And then this is the time rate change of the moisture. And there are some definitions here, which I won't go through. So this system includes acoustic waves. It does not, it makes the shallow atmosphere approximation that I talked about earlier. There's a new version of MPAS that does not make the shallow atmosphere approximation. It's being tested. And it looks like it's going to be fine, but it's not in operational use yet. Okay. Let's talk about the grid, and this will be a relatively long section because this is a subject that I like. So as you probably all know, MPAS uses a geodesic grid. It's a grid that's created by starting from an icosahedron in a way that I'll show you. And the purpose of this slide, which I got from Bill Skamrock, is to compare the geodesic grid here, looks like a honeycomb, right? With the latitude, longitude grid shown on this side. So this is derived, or defined, I should say, by starting from latitude and longitude coordinates. The geodesic grid is not defined by starting with a coordinate system. So sometimes I hear people say, the model uses a geodesic coordinate system. That isn't right. It uses a geodesic grid, okay? In this case, the grid cells are inhomogeneous in the sense that in the tropics they're big, and at high latitudes they're quite a bit smaller in the x direction. It's anisotropic in a sense that I'll define here in a minute. Polar filtering is required because with this grid, the delta X gets very small, so the grid spacing is small in the X direction. You need to take a small time step unless you use a polar filter. Nature doesn't use a polar filter, as far as I know. So that means that the implementation of the polar filter is somewhat arbitrary. There are different ways to do it. The polar filtering can scale poorly on massively parallel machines. The geodesic grid has almost equal area everywhere, as you can see. The grid cells are quasi-isotropic. Again, I'll tell you what that means in a minute. There are no pole problems, and it scales well on massively comparable computers. So there's a list of papers here that dealt with with geodesic grids, starting with this paper by Sidorny et al. 1968, and then Dave Williamson from NCAR independently did it, a paper published in 1970, which is actually mentioned in a footnote in the Sidorny paper. So Sidorny knew that Williamson was working on it at the same time. Then there's some later papers here, including some from my group. And this is Bill Skamrock, 2012. And this Marco Giorgietta is at the Max Planck Institute in Hamburg. And this is a paper from University of Tokyo in 2001. Okay, so you see this kind of took off starting in the late 90s. There was a sort of stagnant period here between 1968 and 1995, and then it sort of took off. So these little diagrams show a grid with triangular cells here. The central one is shaded just to set it apart, so the white ones are the neighbors of the central one. This triangular grid is used in ICON, the German model. This is a quadrilateral grid. It's actually a square grid. It looks like it's on a plane, but something like this is used with a cube sphere. So I'm going to say it's used in CAM-SE and FE3. And this hexagonal grid is used in MPAS and also in NICAM, the Tokyo model. I'm having trouble. Now it's going to be too small again. Sorry. I've gotten lost. Okay, so this shows you how the grid is generated. You start from an icosahedron, the 20-sided platonic solid, and each side is a triangle. And then you subdivide the sides. So for example, this side here has been, you put a dot in the middle, put a dot in the middle of this one, and a dot in the middle of this one, and connect the dots. And that defines 4 triangles, as you see here. And then you can pop that out onto the sphere, so I made it look round now, and then do it again. And you can do it as many times as you want. So you can generate grids of arbitrary high resolution with this approach. It's a recursive approach. And this table lists various grids. So the smallest one that might be useful is probably G5, which has a grid spacing of about 240 kilometers. And then this table shows you G13, which is a grid spacing of slightly less than 1 kilometer. Okay. And of course, you could go higher than that. I'm in trouble again here. Let's talk about the horizontal momentum equation in MPAS. So it uses a geodesic C grid. And many of you have probably heard the C grid and the A grid and all that, but the definition of the C grid is that the normal velocity components are predicted on cell edges. So here's a quasi-hexagonal cell on the sphere for MPAS, and the normal component of the velocity is defined here, and here, and here, and here, and so on. Each edge has a normal component of velocity, and then the centers are called ABC, capital ABC. And there are normal components here among those three as well. So most of the cells on the MPAS grid are hexagons. The vast majority are hexagons, but there are exactly 12 pentagons, which comes from the vertices of the icosahedron. And there are a few 7-sided polygons called heptagons. The grid is trivalent in the sense that every vertex, like here, is 3 edges coming together, okay? Trivalent. The cell centers are the centroids of the cells. Mass is predicted at the cell centers, at A, B, and C, okay? And as I've already shown you, the normal component of the wind is computed on each edge. So the grid is optimized so that cell edges bisect the lines connecting cell centers. So this edge bisects this line connecting A to B, okay? And the lines connecting cell centers are perpendicular to the edges, so this is a right angle here, okay? And those things allow second order accuracy on the grid, okay? They would, in principle, allow higher than second, but second is a minimum. So we need to compute gradients. MPAS uses the equations in what's called the invariant form, the equation of horizontal motion in the invariant form. So there's a gradient involving the pressure, and there's also a gradient involving the kinetic energy. So we want the pressure and the kinetic energy to be defined as cell centers, like here and here, because then we can calculate the gradient here by taking this difference, and that will be defined right where the U lives. So it's very convenient and simple without any averaging. And, okay. There is a problem with the hexagonal C-grid, which is called the degrees of freedom problem, which I'm going to explain quickly. It's important. So let's start with a quadrilateral grid. On a quadrilateral grid, I've got 2 wind components for each mass. The mass is the blue H, and the wind components are the red U and V, okay? Now you might say, wait a minute, there's 4. But each one of these, like this one, U, is shared between 2 cells. So it's 4 divided by 2. There's actually only 2 wind components per mass. But on the hexagonal grid, there are 3, okay? You've got 6 neighbors, and each of these winds, the red arrows, is shared between the central cell and one of the neighbors, but there are 6 divided by 2 equals 3 winds per mass point on this hexagonal grid, and that's too many. There's only supposed to be 2, okay? Because there is an extra component in the wind, there's a part of the wind field that's not controlled well. It's called a computational mode. It's a false solution, and it looks like noise. So you don't want that, but it's a property of the hexagonal C-grid, and it is what it is, as I say. The C-grid also has a problem with the Coriolis terms, okay? Actually, 2 problems. When we compute the Coriolis terms, we have to do some averaging. Let me go back to this slide. Let's say I want to compute the FV term so I can predict U at this point. That's a Coriolis term at this point. Well, I don't have V here. I've got a V here, and there's another one over here, another one down here, and another one over here. So I can average 4 Vs to get a kind of averaged V at the U point. But when I average the 4 Vs, any noise on the Vs will disappear, which means the model doesn't know about it, so the model can't get rid of it. So that's potentially a computational mode issue. That's one problem. The second problem is that in the continuous equations, the Coriolis terms don't affect the kinetic energy because it's V dot K cross V. So V and K cross V are perpendicular, you get 0. But in the finite difference system, that may not be true. So both of these problems were actually solved for the case of a Cartesian grid and a spherical grid. in this paper by Arco and Lamb, 1981. But what was done later and what's used in MPAS is a similar solution on the geodesic grid. And that was described in these three papers, especially the first one. It involves averaging in a complicated way. I'm out of time, basically, but they solved both of those problems. But they did not solve, their solution is called TRISC, which stands for Thuburn, Ringler, Skamrock, and Klemp. But they didn't solve the degrees of freedom problem with this. So regional refinement is something that MPAS can do. It's important. This is the way regional refinement has been done in the past by nesting. You define a local grid with small grid cells, in this case over North America, and larger grid cells everywhere else. So you have a discontinuous change where the fine grid and the coarse grid touch. And that discontinuous change can lead to various numerical issues. What MPAS does is a smooth stretching of the geodesic grid. So you have small cells here over North America and coarser cells elsewhere, and the transition is smoothed. It gives better accuracy. Okay, coming to the end, Peter. Scalar advection, one slide on this. I'm just referring to a paper, basically. So Skamrock and Gassman, German, derived a very nice scalar advection scheme that's used in MPAS, and it's a monotonic scheme, which means that it prevents unphysical oscillations, and it also prevents accidental creation of negative water, for example. It's also quite accurate. So I invite you to read the paper cited here. And last thing is time differencing, one slide on that. I have a set of slides from Bill Skamrock that's got like 10 slides on this, but I'm not going to do that. So what MPAS does is called time splittings. The idea is this. We got these sound waves, they go fast, and because of that, we have to take small time steps. But we don't want to. We want to take longer time steps. But the terms of the equations that allow sound waves are a small subset of the total. So the idea is we'll take small time steps for just those terms and longer time steps for everything else. So there is a computational penalty, but it's not as bad as taking small time steps for everything. And this again goes back to Klemp and Wilhelmsen. It's done in a slightly different way now, but this little figure over here shows in a schematic way how this works. The slow processes other than sound waves are integrated using a Runge-Kutta method, and the fast sound waves are integrated using a forward-backward, which means partly implicit method. So here are the small acoustic steps inside an outer loop for the larger Runge-Kutta steps. And then the scalar transport is done separately after. So these are the papers that describe how this is actually done in the model. And I'm done. So again, I won't read this to you.
So we'll take a couple of questions, and then Dave will also be around during the coffee break.
The degrees of freedom problem, how do you see that in your solution? Can you see a certain wave number?
Which problem?
Degrees of freedom, like the
How do you see that? You see it as noise in the wind field. Yeah.
it doesn't have a specific wave number, it's all
It tends to be close to the grid scale, of course. I mean, that's the nature of noise, right? So small scale noise in the wind field, because the wind field is not controlled. You have 3 degrees of freedom in the winds and only 1 degree of freedom in the mass. There should be 2 winds to 1 mass. So the analogy I like is like too many sheep and not enough dogs, okay? Out of control.
Go ahead. Is there any non-linearity caused by the substepping time splitting?
Well, the short time steps are accurate because they're short. And so the alternative is short time steps for everything,
So it's less accurate than that. But the other alternative is long time steps for everything, and that would blow up. So it's a compromise.
Okay, one more, and then we'll take a break. Go ahead.
Is TRISC used operationally anywhere, and if not, is that considered?
You mean outside of impasse?
Right,
It's
sorry,
used in
I missed
impasse.
that. Okay.
So you mean in some of them?
Yeah.
Not that I know of, but I'm not sure.
Alrighty, well, let's thank Dave again.
Hello. I got a green light. All right.
Alrighty, our next speaker is also an DC MIPper from previous DC MIPs. Peter is a applied mathematician, an expert in numerical methods, and same as me, he really likes Lagrangian transport schemes. So we don't only connect over having the first name, so Lagrangian transport. He's going to tell us there exists something more advanced than forward Euler. So go ahead.
It's easy to knock forward Euler, but it's very simple, which Dave correctly pointed out is always an advantage. So my name is Pete Bosler. You guys are a impressive audience with lots of experience. I appreciate your time. I'm grateful to be here today. I thought I'd start out with a little bit of how I got here and why before we dive into timed discretizations. My bachelor's degree is oceanography from the United States Naval Academy, which meant that after undergraduate, I served for 5 years in the Navy, 3 years aboard ship, and then I was in charge of the anti-submarine warfare divisions. Then I moved to shore duty in Pearl Harbor, which is a fantastic place for shore duty. I worked at the Navy's Maritime Forecast Center doing operational weather forecasting, co-located with the Air Force's Joint Typhoon Warning Center. I left the Navy after my 5 years of active duty, went to Michigan for graduate school in applied mathematics, met Christian there. I was an intern here at NCAR during the summer of 2009, part of the SciParks program. I was a student during DCMIP-2012 as part of the MPAS group, and I visited for a day or two during DCMIP-2016. Since 2014, I've worked at Sandia National Laboratories, and for 11 years, I've been working on algorithms, methods, and software for a couple of multi-scale applications, but I tend to gravitate toward atmosphere and ocean modeling because I have that experience. In particular, I led the project that put semi-Lagrangian transport into the non-hydrostatic CAM model. And as a result of that project, where in E3SM version 1, we could simulate 40 tracers in our operational model, for the same computational budget in version 2 with semi-Lagrangian transport, you can simulate 200 tracers. Now the question is, which ones should you pick? And that's a question for the physicists. So that's how I got here today. A little bit of why is this slide from IPCC. It tells us that the global change in surface temperature, averaged annually, is increasing. We know this, we know what's happening. When it comes to global numbers like this, in IPCC, we see words like unequivocal or almost certain, very cool words to be able to use as a scientist. But those numbers are global annual means. They don't treat Boulder any different than Cairo. So it's hard to figure out what's going on for you and for me and what that means for where we should invest our resources. When we start trying to answer those questions are about regional impacts, and they're much harder to answer. And when you look in IPC for those answers, you see much less impressive adverbs, like medium confidence or likely, like kind of wishy-washy stuff. Those numbers that are global annual means, they're not without meaning, though. They represent an enormous amount of additional potential energy in the coupled Earth system. And so when we're talking about regional impacts, we're asking, what is the implication of all that additional potential energy? For our ecosystems, what does it mean? How, where, and when might it turn into kinetic energy? Because that's a big deal when you see things like this. Super Typhoon Goni in 2020 made landfall with sustained winds of 170 knots, sustained. If you are not a mariner or have not been a mariner, 170 knots is 195 miles per hour. sustained. If we're going to see tropical cyclones like this, or rapid intensification, or with what frequency, we really need good models to answer questions about risk. So that's a little bit about why I like to do what I do. And today's talk, we're going to divide into a couple of different sections. I'm going to start out with an introduction to time stepping, kind of how we as a practicing community of modelers got to where we are today. We're going to look at the anatomy of a time step in a modern Earth system model. From there, we're going to go a little bit, take a few steps back, look at the fundamentals. Always good to look at the fundamentals. But at a workshop like this, I think it's important not just to review the concepts behind what we do, but also to see how they're used in practice. And so we're going to come back into some of the more modern things that we're actually doing in the past couple of years. So the fundamentals, probably a lot of you in this room will have seen before. Bear with me through that if you find it not so interesting. We will get to the new stuff, which includes some of my group's papers, which I know that very few people have actually seen. It's been a while since I gave a lecture like this, so I did some homework. My name is not on the DICOR book, but there are 2 chapters that are relevant to this seminar, 5 and 6 by Dale Duran. The blue book in the middle is a new 2nd edition from Cambridge. It's really nice to read as a numerical weather perspective. And it has a nice section on data assimilation. And then I learned a lot of the stuff that I'm going to talk about today from Randy Levesque's book at the bottom, which Owen also mentioned. So that's where most of this stuff comes from today. I'd like to start out with a little bit of history, since we're kind of repeating ourselves a little bit. In 1904, Wilhelm Bjerknes from Norway came up with an idea of an atmosphere model. And even 120 years ago, they knew what the equations of motion were. I would call them Navier-Stokes, specialized to the atmosphere. Bjerknes felt that you just can't solve them, not in a reasonable amount of time with a good enough accuracy, so let's not even attempt to do it. Let's do a graphical forecast approach. Let's write down, or let's draw the charts from all the observations we have available, and then humans are pretty good at pattern recognition, so if we can see the patterns on a surface chart for each level, we can prognose that chart forward graphically and stitch those time steps together to generate a forecast. That's actually what a lot of meteorology students learn. It's what forecasting was through the 70s before numerical weather prediction really took off. And if you're paying attention to, if you can teach a computer how to do that, you get a Nature paper. That is exactly what the Microsoft Foundation model does. They figured out a way to take lots of atmospheric data and write it in a format that is recognizable to image processing algorithms. And then they can leverage all of the machine learning methods that have proven successful for image processing in the context of atmospheric modeling. Bjerknes inspired a very interesting man named Louis Fry Richardson, 1922. He was a British pacifist who refused to serve in the military during World War I, but he wasn't trying to get out. He just didn't want to be part of violence. The Brits prevented him from holding an academic position for the rest of his career because of that, but he wasn't trying to get out of service, so what he did instead was he went across the channel and drove an ambulance for the French infantry during the war, which is relevant because when you read the preface, you see 2 interesting things. Number 1, he credits his wife with doing all the integration of the boundary conditions and observations from balloons. Number 2, you find out that he lost his manuscript during the war. The front moved, they had to go with it, and when he came back, it took several months to find his atmosphere model buried underneath a pile of coal. So it took him several years to publish this, but he did in 1922. It's the first real numerical weather forecast model that we do recognize as like the stuff that we work on. What he called computing forms, we called finite difference operators, and we're going to talk a lot about those today. What's interesting is that his work was described as a catastrophic failure and scientifically impeccable. I find that juxtaposition pretty interesting. Failure because it didn't work. He predicted a very unrealistic change because he didn't know it at the time. Finite differences were just being invented. He found an instability. Fast waves polluted his solution. He predicted a change that was almost impossible to actually happen, And his forecast was so wrong that it discouraged people from attempting numerical weather prediction for another few decades. Nevertheless, as recently as 2006, if you read his model, it's a complete model. Soil moisture, balloon observations, all put in together with a reasonable discretization of the equations of motion. So really interesting guy. Where we are today, using tools that Richardson did not have available, are a very complex situation. These are the non-hydrostatic equations of motion that the CAM-SE model solves from Mark's paper here, and we time-step them in a very complicated way. We do something called heavy, horizontally explicit, vertically implicit. We use a separate horizontal and vertical discretization like Dave talked about. The transport scheme, which involves equations like the bottom one, is a semi-Lagrangian transport scheme for reasons of computational efficiency and accuracy, but that introduces complications because now we're solving the dynamics with one method and we're solving transport with another method, and they both have their own notion of air density. Those have to match. And then on top of all that, these are all coupled separately to all the physics parameterizations. So I'm not just an alumni of the University of Michigan, I'm actually from suburban Detroit. We tend to use car analogies for almost everything. What you see when you look at a climate model is a time step that looks like this. There's physics and transport, which is expensive to compute, so we do it slow, because we don't want to do it too often. But just like a car engine, you have quasi-independent components all synced together. The dynamics is time step quickly because of waves and computational constraints that we'll talk about now. And when we put in semi-Lagrangian transport, it turned out that our vertical discretization with the floating levels did not like the long transport time step. Levels could collide, so we had to go back and pull that out into a separate vertical remap time step. So that's where we are now. And when you see the code and you look into it for the first time and you see something that complicated, it's reasonable to ask how much of that complication is necessary and how much of it is just there because it's in the code and we're stuck with it. Those things exist. And a lot of this complexity is the result of a lot of good work over decades by a lot of good scientists. So it's hard to sort out in some cases. It turns out that numerical stability is a nuanced and challenging concept to define. And that once we do so, we can design mathematical methods that are really good, and even though they're very elegant mathematically, they can be too computationally costly to use in practice. And so these mathematical ideals sort of get polluted, if you want to take a math point of view, by reality about we need to be able to compute an operational forecast every 6 hours for a weather model, or the sheer computational load of a climate model where we have an atmosphere and an ocean and an ice and a land ice. You need the same kind of throughput that you need for numerical weather prediction. So we end up with competing concerns of accuracy, conservation, shape preservation, and computational cost. And the balance of these decisions is different when you're working on weather than when you're working on climate. When you're working in weather, you can prioritize accuracy above everything else, right? Truncation errors in total mass, for example, don't add up to very much over a 10-day forecast. But those small errors over a decades or centuries-long simulation in a climate model can add up to the point where you're not simulating Earth anymore. And so you tend to prioritize conservation in climate models. When you get into a room like this with people like us that spend our days trying to make our models better, which means that we have to think about how they're wrong, it's easy to think that models aren't very good. So I like to put this slide up when I give a talk like this to remind myself as much as everybody else that models are actually really good, and we've made lots of progress. So this is a chart showing the track error, the location error in tropical cyclone forecasts for the Western Pacific for the last 50 years. You can see decrease in error over that time due to better computers, better algorithms, better data assimilation. The orange slice there is when I worked at JTWC. There's a local minimum there, but let's not read too much into it. What I like to do is put a horizontal line here. And we can see that over the last 20 years, 2020 is the most recent version of this annual report that I could find for today's talk. But over the last 20 years, we see that the 72-hour forecast has become as accurate as the 24-hour forecast, which is a very impressive improvement in quality. Okay, so that's kind of the state of things. Now we're going to start doing some fundamentals. When I tried to figure out if I was to talk about time discretization to a new audience, let's write down all the stuff that we use to talk about such things amongst ourselves in our meetings. And it's too much. We're not going to be able to do all this. So these are all the vocabulary terms I sat down and brainstormed. It's an incomplete list, and we're not going to get there. Some of my favorite things we're not even going to have time to get to today. But we're going to make an attempt. And so I thought I'd introduce some notational conventions. These follow Levesque's book, the blue one from the slide a few slides ago. Notation is really hard, and it's really important, and good notation makes a big difference. Try multiplying Roman numerals. So the convention from Levesque's book that I find helpful to use is where I'm going to use the letter J or I to do spatial discretizations in the subscript, and the index K to do time indexing in the superscript. So immediately we have a notational conflict with superscripts and exponentiation that will hopefully be highlighted in red when it happens in a few slides from now. But the advantage of this method is in this bottom line here. The solution U, our approximate solution at grid point J at time K is just UKJ, really easy to write down. And then we can compile all grid points J into a column vector, which I'll use capital U, again at index K in the superscript. We're going to talk about finite differences, which is where Richardson started, but also because if we start here, we get all the analysis and theorems that apply well to spectral element methods or finite volume methods. We can sort of learn everything we need with these pieces right here. So we have the definition of the derivative, which we all seen before. You do what you do in Calc 1, and you take a small number for the step size delta x, you plug it in, you get an approximation of the derivative. So if you take that step forward or to the right, you get the d plus operator. If you use a minus sign to the left, you get the d minus operator. You can average those two and get a centered approximation of the first derivative. You get d0. And you can compose those two together and apply d plus to d minus or the other way around, and you get a centered approximation because the plus and the minus average out. But now, since you've done it twice, you get an approximation of the second derivative. You can figure out how these are accurate by looking at Taylor series. So Taylor series are going to be fundamental to everything we talk about today. You can remember that for a smooth function, it's defined like this, and in finite difference analysis, we just play with adding the Taylor series together and getting terms to drop out, so we minimize error, hopefully. So what you do to figure out how these discrete operators work is you take what you have in red, and then you look at everything that's left over. And hopefully you have what you want, plus stuff that's small. So here we have a first derivative approximation, and if delta x is small, then the leading term is also small. And we can do that for the second derivative too, and we get something like delta x squared, which is even smaller. So that's pretty good. We end up with something that looks like this for each of these operators. The d plus and the d minus have delta x to the first power, so we say they're first order accurate. The d0 is a second order accurate approximation of the first order derivative, and then the d squared is a second order approximation of the second order derivative. It turns out that those leading error terms are really important, so we give them our own name. We call it local truncation error, and we give that the symbol tau j. Tau for local truncation error, because fundamentally we've derived these operators by truncating the Taylor series and using that to approximate things. So the d plus is a first order tau j, the d0 is a second order, same symbol tau j, and in fact the truncation error stays the same, symbol anyways, even when we're approximating the second derivative. The idea is truncation error is the leading source of error from how you've chosen to approximate your derivative. Truncation error is easy. What we really care about is global error, right? We want to know what the solution is at some fixed time t in the future, no matter how many steps it takes to get there. So we say a method is consistent, which is easy to show if the truncation error goes to 0. Global error is what we really care about, and it's a function of the step size, right? How many steps does it take to get to that time t? And what we really want when we derive methods like this is something called convergence. We want global error to go to 0. And it turns out that consistency by itself is not enough. You also have to have stability. And stability, as we showed when we talked about Richardson, is kind of tricky. Intuitively, a stable method is a method that does not amplify error. Right? Dave's talk, he said that it's really bad when error gets worse as you increase resolution. That is a manifestation of instability. In some cases, But let's look at it from this perspective. At any point in time, here at time 0, our computed solution can be represented as the exact solution plus some error, okay? So then we apply our numerical method to advance to the next time step, and we apply it to everything, the exact solution and the error. And we get a new piece of error from applying it again. So we get the error at the initial time plus the error at the next time, and then all of that goes inside the next application of error. So if this method is unstable and it amplifies error, every time we apply our numerical method, we're potentially making the situation worse. So a stable method, we don't make that situation worse. Error stays bounded, we get a convergent method. So intuitively, a stable method is one that does not amplify error. It's a good kind of rule of thumb to keep in your head without getting into too much detail. Sometimes I don't like myself. I just said, let's not get into too much detail, and then I put up a slide that has Lipschitz continuity. We're not going to talk much about this, but I'm from a math department, and I couldn't not. You have conditions on differential equations for the differential equation itself to have a unique solution, and there's no point in approximating something that isn't well posed, so I felt I had to do that. What we really care about, though, for this seminar is, can we use our finite differences to approximate solutions when they exist? And so can we use our differential operators, the d plus, the d minus, the d0, et cetera, to march a forward, or march a solution forward in time? I really want to get to some new results and not just some fundamentals, so I'm going to go through the next few slides really quick. If we use the d plus operator and we apply it, we get what's called the forward Euler method. You probably all saw it in Calc 2. It's very easy to write down some vocabulary. It's an explicit scheme because the next step is given explicitly in terms of steps that come before it. If we do leapfrog method, you can derive that by applying the d0 centered operator to your differential equation. You get a multi-step method because now step k plus 1 depends on step k and step k minus 1. They're not self-starting, right? That formula tells you how to get to step 2 from step 0, but it presumes you already have step 1. So you have to figure out how to get step 1. If we apply the d minus operator, you get what's called an implicit method, because when you go backward differentiation, the k plus 1 step appears on both sides of the equation. It's implicitly a function of itself. Those methods always have an extra solution step. You have to figure out how to get the k plus 1 out from both sides of those equations, usually iteratively with something called Newton's method. It's worth asking why you would put up with that extra step for an implicit method. We'll see why later. And then there are other methods that are a little bit more tricky to relate to Taylor series, but they're very cool. Runge-Kutta methods, for example. You can be multi-stage without being multi-step. And you do that by introducing intermediate steps in time. Here, there's sort of a midpoint in time, and you use that to get better accuracy. You can still show it's a one-step method, right? If you combine these two lines into this line, you can clearly see that k plus 1 depends only on step k. So it's a two-stage, one-step method. Turns out you can do that lots of ways with Runge-Kutta. And up until 2019, we used a third-order Runge-Kutta scheme for our hydrostatic dynamical core. There is a nice parsimony here between two stages and second order, and there is a three-stage third-order Runge-Kutta scheme, but we used a five-stage third-order Runge-Kutta scheme. It's worth asking, since the amount of computational work is proportional to the number of stages in a Runge-Kutta scheme, why we did that, and the answer is we got better numerical stability. So even though there's more work per time step, we are able to take larger time steps, so fewer time steps overall, using that five-stage third-order scheme. So here's a illustration, probably similar to several you've seen already. We can put these methods, code them up in a Python notebook, and plot their solutions, and watch what happens as we decrease the step size way up there in the upper right. So the second order methods collapse pretty quickly onto the exact solution, and good old Euler starts catching up as we get to a small step size. But let's take a look at the final time and look at what happens to global error as we keep decreasing the time steps. So now we look at a log-log plot where the slope of these lines is an indication of the order of accuracy of the method. So the 2 second order accurate lines fall on the second order slope, and Euler falls on the first order slope. So graphically, these things appear to converge. We know we can't use graphs as proof, but they are evidence. I wrote down the proof for convergence of Euler. It's 6 slides and boring, so it's at the end if you want to see it. But I'm going to skip it for now. What's nicer is to ask, well, but before this, nicer. I like horizontal lines on graphs. You can ask yourself, if you have an error threshold for a particular application, how many steps does it take to get there? And you can see quickly the advantage of high order. It only takes 64 steps for the 2 second order schemes to get to a relative error of 10 to the minus 2, but it takes 2,000 steps for Euler to get there. So again, it's easy to knock on Euler, but it is simple, so it's a good place to start. We don't want to have to prove convergence with 6 slides for every scheme. So we have some nice work from a lot of mathematicians in the middle of the last century. Peter Lax just died recently, some of you may have met him. He was giving talks as recently as 5 or 10 years ago. But the fundamental theorem for numerical methods for PDEs is that consistency and stability is equivalent to convergence. And that equivalence significantly goes both directions. So instead of having to prove stability for every individual method, if you can prove a family of methods is convergent, then you know they're stable. Or if you can prove a family of methods is both convergent and stable, or both stable and consistent, then you automatically know that they're convergent. You can do that proof once, and then it works for the whole family. That tends to be one of the things we like these theorems for. Now we can start to talk about some definitions of stability that are a little bit more precise. So we have this idea of a test problem that's really important. We want to choose a test problem that is simple enough to be easy to work with, but complex enough to show us interesting things. That's also a theme at this workshop, right? We have squall line, gravity waves, and gap flow, all test problems. The test problem we're going to use here is very simple. It's this first order u prime equals lambda u, but we're going to add some complexity by allowing that eigenvalue lambda to be a complex number. So we can get both first order dissipation, but also some oscillations in waves. And we're going to define this amplification factor as the one-step proportion of the k plus 1 step solution divided by the k solution. For forward Euler, it's very simple. You have the k plus 1 is 1 plus lambda delta t for that equation. You just divide by uk, and you get that the amplification factor is that 1 plus the eigenvalue times the time step. We can define a method as being absolutely stable if that amplification factor is less than or equal to 1, if it lies inside the unit circle in the complex plane. And then we can make some pretty plots to give ourselves some good graphical intuition of how these things work. So we can define a stability region for a particular method as the region of the complex plane where this product between the complex eigenvalue lambda and the real number time step delta t are all amplification factors less than 1. And you can plot these things. For forward Euler, you get a circle of radius 1 centered at z equals minus 1 on the real axis. For backward Euler, you get everything outside a circle of radius 1 centered at z equals 1 on the real axis. And that is why implicit methods are worth paying the price for in a lot of cases. They have very good stability properties. And then the Runge-Kutta second order, Runge-Kutta fourth order are plotted there. When we start talking about advection problems, we're going to need to know which of these stability regions include the imaginary axis. And it's worth pointing out that forward Euler does not. So that was just regular differential equations. We are interested in solving partial differential equations. The easiest way to connect those two things is to use something called the method of lines. So we have just one dimensional space, so we can draw the xt plane. And so if we discretize in space, we have grid points xj on the bottom. You draw a vertical line. That line represents the evolution of the solution at grid point j, moving forward in time. You get method of lines. What you can do with method of lines is collect all your solution u into a column vector capital U. And if we apply to the heat equation, for example, here, you end up with the same kind of test problem we were just looking at, except the matrix A is down there instead of the eigenvalue lambda. And the matrix A depends on the discretization you use in space. So if we do the second order centered second derivative approximation, you get this matrix here. And now you can see how time step and spatial steps are coupled, because delta x squared is here in the denominator. So the system size grows as we resolve in space. As we decrease delta x, we get a larger matrix, and we divide by a smaller number. And I just said that, so let's keep moving. The eigenvalues of this matrix happen to be on the real line, all less than or equal to 0. But their amplitude grows as the inverse of the spatial step squared. And in order for our partial differential equation time stepping with both the space and the time to be stable, we need to be inside the stability region for the particular time stepping method we chose. So if we plot all of these lambda times delta t numbers as red circles, we can look at where they fall with respect to the stability region of the time stepping scheme. And here, even with a time step that's 10 times smaller than the spatial step, we can see that we're not in the stability region. You can get there, it takes a very small time step. And now you're spending a lot more work computing time steps relative to the amount of work you're investing in space. So it's kind of an imbalance that is unattractive computationally. You can switch to backward Euler, and you get stability almost for free. And now you can choose your time step based on error and accuracy instead of stability, which is really nice. The heat equation is kind of a nice place to work. We work on a little bit more of a hard problem, the advection equation, often cases. It has some interesting properties that are worth reviewing. Again, the xt plane. So the advection equation, we know, especially in this linear equation, linear one-dimensional advection, the solution just moves forward along the, yes? Sure.
I think, so for the eigenvalues for backward Euler, I wanted to be like 1 over the eigenvalue, or
when you like want to satisfy the stability constraint, so wouldn't you want your eigenvalues to be greater than 1? So it's 1 over like something greater than 1.
I'm not sure.
Let's talk about this after.
Thanks. I may have made an error just for trying to come up with a simple illustration. But the take-home message is implicit methods tend to be more favorably stable. That's why they're worth paying the price for the extra solution step. Okay, advection equation. The solution moves to the right without change in shape, without change in extrema. There's an important thing you can talk about in advection equations called characteristic curves. These are the curves. In this case, the solution stays constant along these characteristic curves. These curves are the reference frame that semi-Lagrangian and Lagrangian methods use. And you can get very stable and very accurate accuracy with those methods, often at the cost of having to do a little bit more, or sometimes a lot more geometry computations. But it tends, in my experience, to pay off. Another thing that's kind of interesting about advection is that it's a partial differential equation whose solutions can be not differentiable. So, let's not spend too much time on that, though. Instead, let's put our discretization down and come back to our discrete operators, d plus, d minus, d0, and d. And we're not going to need d squared because we're first order in time now. Now let's look at what happens when we start applying these. So if we apply d plus in time and d minus in space, we end up with what's called the upwind scheme. Since the advection in this problem is to the right, the stencil is oriented to the left. That's where we get the upwind term. And the stencil here are the grid points that represent the data available to each grid point during one time step. If we apply d0, the centered second order operator in both time and space, we get this stencil, and we get something called the leapfrog method, because we skip the actual grid point that we're at, right? Leapfrog. This number in blue is important. We're going to give it a name in a second. It's called the Courant number. And then you could do, we know that centered finite differences tend to give better accuracy than one-sided differences. So we might choose to use a centered approximation in space and a forward approximation in time. And you have a stencil that looks like this. The Courant number is an important number because we want the stencils to always be using information that they have. So there's this thing called the Courant-Friedrichs-Levy condition, which says that you don't want information in the continuous system to be able to travel faster than information in the discrete system. So in other words, you want the characteristic curves to lie inside your stencil. If you've satisfied that, you've satisfied the CFL condition, and you have reason to believe that your method should work. So we can write up a notebook and put all these things together, and we see some differences. So upwind's on top, the exact solution's in blue, the computed solution is orange, leapfrog's in the middle, and that forward in time centered in space is on the bottom. So upwind, we see its solution's in the right place, but it's shrunk, it's dissipated. Leapfrog, the well-resolved peak is where it's supposed to be with the right amplitude, but the moderately resolved peak still has the right amplitude, but it also has these squiggles and it's slightly in the wrong place. That's called dispersive error. And then the forward in time centered in space scheme has just blown up. That's what happens when you have an unstable scheme. So all of these schemes were consistent. Their truncation error went to 0, and the CFL condition was satisfied. So stability is a little bit more than you might initially guess, which, you know, too bad for Richardson. That's unfortunate. So dissipative error up there, dispersive error in leapfrog, and then instability in the forward. So why is the forward in time unstable? When you write the matrix out for that spatial discretization, you get a matrix that's skew symmetric. And when you have a skew symmetric matrix, all of the eigenvalues lie on the imaginary axis. There's no real number, delta t, that we can multiply pure imaginary numbers to get inside the stability region of forward Euler. That method turns out to be unconditionally unstable, no matter how small a time step we use. Dissipative error is too much smoothing. It destroys, well, it doesn't destroy them. It just smashes down extrema. We get error from smoothing that is not physical. Dispersive error, you can kind of think of as the waves might have the right amplitude, but they're in the wrong place. Dissipative error, the waves are in the right place, but with not the right amplitude. And both of these errors can depend on the wave numbers in the solution. Okay, so review of fundamentals. I'm getting close on time, so we're going to sort of leap forward 50 years. Instability in practice. We are still seeing these challenges today, and the way they show up is noise. Noise that grows. And when you find them, you have a couple of things that you can do. You can try to stabilize fast waves in the equations themselves by introducing approximations like the Boussinesq approximation or the anelastic approximation. You can try to stabilize the numerical method after discretization by adding dissipation. We use hyperviscosity in CAM-SE, for example. Or you can choose a new or different numerical method, which is when I normally advocate for Lagrangian methods. Some things that come from our experience working with CAM-SE. When we switched from hydrostatic to non-hydrostatic 5 or 6 years ago, our analysis suggested that our time step should be stable, but our solutions were showing instability. Now we're back to the question of test problems. The test problem that we were using to say that our method was stable is this 2D acoustic system. Acoustic waves in the XZ plane. We were suggesting to ourselves that if we plot that stability region up there in white, if our time steps all fall within that stability region, our method should be stable. We're using a bad tool for the non-hydrostatic equations. So we changed it. We switched to a 3D linearized Euler system. And when we look at the stability regions using this test problem, you find out that the stability region in white is much smaller than what we had been intuitively using from our hydrostatic test problem. So we wrote this up in a 2020 paper, and then we used this tool to derive better time stepping methods, because it turns out that in order for the 5-stage third-order scheme to be stable, we had to use a time step that was so small, the non-hydrostatic model became very expensive relative to the hydrostatic model, to the point where people wouldn't want to use it, because it would just take too long to finish computing. So we switched our time stepping schemes. So we switched to one where we kept third order accuracy in the explicit terms, and we chose to treat the vertical terms associated with acoustic and vertically propagating waves with a second-order implicit method. So we end up with more buzzwords, IMEX for implicit-explicit splitting, or HEAVY for horizontally explicit, vertically implicit. But the punchline is, when we switched, now the non-hydrostatic model can use the same large time step as its hydrostatic predecessor. Another example came when we tried to put our semi-Lagrangian transport scheme into the dynamical core. We got stuff that looks like that. So in this test case, 2 slotted cylinders deform and move around the sphere, and we had semi-Lagrangian time stepping. It's supposed to be stable. We had a spectral element discretization in the horizontal for space. That's supposed to be good, but we were getting stuff like this. But we weren't getting it all the time. We were getting it intermittently, which was puzzling in some ways. So even though advection is a linear problem, it's still difficult when the velocity is variable. So we couldn't write down the eigenvalues ourselves. We did code up a way to approximate them numerically. And so on the bottom here, we're showing the difference between the maximum eigenvalue of our numerical method and 1. Remember, we want to be less than 1 to be stable. For many choices of time step in the red box, we're basically at 1 to single precision. And the method is right on the borderline of stability. But you can see that for some choices of time step, we are far outside that red box, and we are actually unstable. When it comes to tracer advection, we know there's a few other things that we want from our advection solution, right? We want it to always be positive. We want concentrations to never go above 1. And so we put on shape preservation filters for those kinds of things. And you automatically get boundedness, but you've also made your scheme nonlinear. So this linear stability analysis that we've been showing doesn't really apply anymore, but you still see the noise even in the limited solution up there on the right. So going nonlinear can't recover from the problems of instability. What we did to fix it was we decided that the instability was caused between a mismatch of the time discretization and the nodal polynomials of our spectral element method. So we came up with different polynomials. We call them stabilized bases. We call the method islet, interpolation semi-Lagrangian element-based transport. And so the scheme itself is described in this 2022 paper, and the way that we found the stabilized basis polynomials is a 2024 paper. So this work is all happening still, even though stability has been a problem since 1922. I went really fast. We covered lots of ground, but I wanted to leave time for questions, so we hit a few of these.
Yeah, so I guess kind of similar to the islet plot. Earlier on when you were talking about RK3, so you mentioned multi-stage methods. So for those stages, I know you guys use Gauss, Legendre, Lovato for spatial. How do you decide where to put those stages for a multi-stage method?
So when you start using Runge-Kutta methods, you have this thing called okay, so first of all, there's 2 different things going on in your question. The GLL polynomials are spatial discretization. And where you choose to put the stages for Runge-Kutta, that's time discretization. So we can answer those separately. With Runge-Kutta methods, you have something called the Butcher tableau. And when you write down the formulas for a generic Runge-Kutta method, you can write down conditions in this table that the coefficients have to satisfy for a given order of accuracy. And that's where the stages come from. They come from those tables. With respect to the stabilized basis, Andrew wrote a program that searched the polynomial coefficient space for polynomials that were of the same order of accuracy that we wanted at the cost of adding an extra node or 2 to our element. So we only use those polynomials for the transport scheme. The dynamics are still the standard Galerkin spectral element polynomials.
Yeah, thanks for the talk, that was awesome. So you developed this heavy scheme for the non-hydrostatic case, and I was just curious if it led to any savings, or did you implement it for the hydrostatic case as well?
It's now in there and a choice for both. The savings, I think it took our non-hydrostatic model from like a 5-minute time step back up to a half-hour time step. So, is that close to right?
I think the question was, does this scheme, did this scheme help the hydrostatic model?
Oh, well.
And I think the answer to that is no, it didn't. It was necessary to get the non-hydrostatic competitive with the hydrostatic.
The hydrostatic scheme was still a 5-stage third order. This is implicit, so now we have solves. Dirk solves, diagonally implicit Runge-Kutta. So now we have an implicit method, we have an extra solution step that you don't need to do the hydrostatic model, right? Yeah. Yes?
Yeah, this is about the 1D advection problem. So it looks like when you have like the dispersive or the dissipative errors, like you're definitely changing like the underlying spectrum of your solution. But I was wondering like what happens if you look at like the norm or like the energy of the solution? Like does that increase or decrease?
So for leapfrog, the norm stays the same because its eigenvalues are imaginary. So you end up with dispersive error that's not dissipative. That's going to be a different answer for every different scheme. And some schemes have a little bit of both depending on how complicated they are. And then you have to remember that your test problem is linear advection, and we're solving nonlinear advection in practice. It still tends to hold up pretty well.
So this is more of an open-ended question, but I guess going back to when you talked about Runge-Kutta as an example, so how do you figure out how to trade off stability and performance, right? Like you can keep going past RK3 if you really wanted to. RK4 might be more stable, so I guess where do you call it quits and just say this is good enough?
So the answer for E3SM, everything has to fit in GPU memory. Everything has to be very fast. Our computational goal is 5 simulation years per day for the coupled model. We're at 1 now, using 24,000 GPUs. So it has to be fast and good, and sometimes we prioritize fast over math good. Like for example, in second order accuracy is high enough, right? In the math department where I learned numerical methods, second order was not good enough. But in this paper, if you choose to read it, you'll see how we did the analysis. So we didn't just look at stability regions like this, we looked at dispersion relationships to see amongst the schemes that were good candidates based on stability, which were the least dispersive in their error characteristics also. And that's how we ended up choosing the one that we use now.
Follow up.
Oh, sorry, go ahead.
Just like then, to what extent can the idealized test cases basically indicate the quality of the solution for a full dynamical core?
The test cases for transport and for dynamical cores are essential. Really, really good test cases. Both from the very simple ones that are just solid body advection around the sphere, you find a lot of bugs, you save yourself a lot of headaches by running those tests at the beginning of your effort. And then you can level up to computational chemistry tests where 2 nonlinear correlated tracers are nonetheless conserved in sum, and you can look, there's all kinds of test cases that a lot of people in this room have developed that are very, very good, that I would say, please do.
You explained a problem where there was like the spectral artifacts or the instabilities appeared intermittently. Could you explain like it happened for some initial values and not for others, or sometime during the time series?
So the analysis that I showed today was for linear advection, so constant advection velocity in 1D. In the problems that we're doing, our velocity is changing in time and space. And so there are, if we want to look at it from the point of view of linear advection that we showed today, sometimes in space we'll have a nice table time step, but somewhere else in the domain the velocity could be very large and we could have an unstable time step locally. And that shows up with those kind of things there. So It shows up there because that's where the shear in the velocity is the largest, right? It's not due to the cylinders, it's due to the velocity that's making the cylinders look like that at that point in time.
Instead of checking consistency and stability, do you ever check convergence directly through something like manufactured solution or something like that, or is that not?
You can.
Okay.
It's a very direct approach,
Yeah.
which is worth trying. But when you start to get out into higher dimensions and more challenging problems, even that can be pretty hard. So, like for our semi-Lagrangian transport scheme, you can abstract everything out into this linear advection operator, and since it's a linear problem, you can, if you write everything in terms of this mathematical abstraction of an advection operator, then you can prove that that operator is bounded, and therefore every form of advection scheme that you can write in that abstraction is stable, and that tends to be, I don't want to, more in line with our mathematical training, right? Now we've proved it for every scheme that can be written in this way. And we can just choose one of those from that family and know that it's stable.
So with semi-Lagrangian advection, there you sort of have two components. You have the Lagrangian step and then you have the remap step. And so are those two things almost always decoupled, or is the analysis sort of closely tied to properties that you want from remap as well? Or?
So the remap step, so there's two different flavors of semi-Lagrange. There's flux form semi-Lagrange, and then there's remap form semi-Lagrange. We chose remap for reasons of computational speed. Right? If you have flux form, you're adding flux to one cell, you're subtracting it from another, you're automatically locally conservative, which is always good. In remap form, you have to have a conservative operator, which is a little bit harder because now for spectral element method, we're doing element, like basis matrix products. And under some conditions, those are conservative. Under other conditions, they're not. It's a little bit harder. But the local region that you have to remap when you're in a parallel computer and to the point where one MPI rank is associated with one element, you want those local problems to be small. With a remap form semi-Lagrangian scheme, you can keep those local regions small. Whereas in a flux form, if you really start pushing the time step large, your flux region can move across several different elements and several different processors, which is why we chose not to do that. So we gave up automatic local conservation. We still have assured the global conservation, and none of the atmospheric scientists noticed. We told them, right? We said, here's a method that's globally but not locally conservative. Is it okay? And we ran every test we could think of, and it was okay. Here.
What's the maximum Courant number you see in like a 1 degree long simulation for similar transports?
In practice, we use a Courant number of 8 for advection. That keeps our communication within one element neighbors. But we've run tests out to 14. So you can really speed things up. Communication gets a little bit harder there, so we had to rewrite some MPI to do that. But it's pretty cool.
So it stays within the neighboring element?
No, then it moves further away.
So that, with the default configuration, does it stay within the neighboring element?
That's where the number 8 comes from. You can move, right, the spectral element, there's 4 grid points per edge. So a Courant number of 8, you can move at most 8, you stay within the one halo. Christian?
I guess I learned that there's even a better advection scheme now in the spectral element dicore, which is even twice as fast. I'm not certain that I catch this right here, maybe. I just wonder whether you can shed light on that or...
Are you talking about the interpolation versus cell integrated?
It's the 2-cell one where you go, I think you said 14, can go up to 2 cells. But the trajectory used to be, there were error in the trajectory calculations that Andrews have improved.
Yeah, so our first trajectories were based on this horizontal discretization, vertical discretization splitting. So we did 2D trajectories on each level with a separate vertical remap. To go out that far in time, we now have to do fully 3D trajectories. And Andrew's figured out how to do that accurately, so we can push the time step even further.
Is that available in E3SM? Alrighty.
Kind of a silly question, but something that I've thought about is any comments or thoughts on spectral element in time? So like a space-time spectral element discretization?
No.
All good. It's just one of those things of like, oh yeah, if we did this in space, what if we did this one way in time? Sort of thought. And somebody with many more years under their belt than me in this sort of thing.
There are some ways to prove stability of these advection operators using space-time spectral element bases. When I wrote the paper, I chose to do it with the Lagrangian flow map, which seemed much simpler to me than appealing to these function spaces that have both space and time high dimensionality. But those papers exist.
Thank you.
Can you observe the orders of convergence in the actual models? Like, if you have RK2, is it second order time convergence?
So time convergence we have shown, even with coupled physics. And a lot of the DCMIP-2016 tests were designed to show those kind of things. Space convergence is harder because of the things Dave was talking about, how the slopes get steeper as we resolve them. More generally, in a flow with cascade to small scales in entropy, you start to resolve more vortices that aren't there in the coarser solutions. So spatial convergence is harder to show. As far as one of the things you can do with our ILET paper is you can really crank up the order of accuracy of the transport spectral element basis. So you can use, for example, like an 8th order spatial discretization. But it's still coupled to a cubic dynamic scheme. So you don't get any better slope in those, convergence plots, but you do move down. So you're not improving the rate of convergence, but you are improving the accuracy.
Okay, let's
Thanks for your
thank
time.
Peter again. Alright. Last but not least, our overview talks, design of the course with Christiane. There's just one. You wanna?
All right. Well, one more to go, and maybe be reminded, please, after my lecture, don't head out and run to the cafeteria. We want to actually do a group picture. And we want to do it actually here on the staircase. I think we might fit nicely, and everybody's visible. So yeah, don't run. Yeah. So let's just go out for a few minutes. I don't think it will take long. Do a group picture and then head out for lunch. Maybe as a heads up, we are dealing with a major crisis actually with Casper right now. Yeah. So nobody, as you might know, nobody has access to the machine right now. It's unclear whether we have it in the afternoon. Let's just see. We are thinking about some backup solutions, so there will be something for us to do. Yeah, we are not 100% sure yet what it will be. Yeah, all right. Okay, I think now is the perfect time really to talk about diffusion, and everybody was setting the stage for me, including Dave and Pete actually. I pulled here for my intro slide actually a slide here from a publication by Biscamarok, and this is showing you the impact of diffusion on the flow field. This is actually a baroclinic wave test case, and you see, basically the baroclinic wave in both, but you see really clearly up here the noise issue that comes up, which can be battled with diffusion, and that's really what this talk is about. Yeah, so I will be presenting many different tweaks which we have available to us, especially in the NCAR model. So I tailored this talk really towards FE3, MPAS, and SE to really give you a little bit of guidance, once we are back on the machine, to even let you test these diffusion options so you get really hands-on information doing that. All right, okay. Why is this even needed? If you want the details, maybe let me just point you to this book chapter. This is a book chapter we wrote after DCMIP-2008, 2008, when I gave maybe the first lecture on this ever. And this was a starting point, since we were writing up the lectures, to really engage deeply into that topic with Dave Williamson here from NCAR. And we ended up writing 114 pages about diffusion. Yeah, so this is everything you might want to know, and maybe there's even more now. Which back then we really did a deep dive into the literature. But let's maybe set the stage. I want to just say that you always, let me see what I can manage. You always need diffusion, no matter what. Yeah, but the diffusion might come in different forms and shape, but you do need it because, and this is kind of something I grabbed from a book by Kalnay. This is really schematics, kinetic energy spectra. You probably have seen this. I think Adam showed kinetic energy spectra earlier this week. Here you see kinetic energy spectra. Here you see wave number, and I labeled this split. So wave numbers in this domain here are large, and then as you go over, you go into smaller and smaller wave numbers, smaller scales. And at some point, you hit the truncation limit. You have 100, for example, 100-kilometer grid spacing, and that's it. Yeah, so you cannot really resolve anything smaller. And well, nature isn't stopping at 100 kilometers. Yeah, you do actually also, via nonlinear interactions, you generate, even with large-scale flow, you generate small-scale things that are way smaller. And I mean beyond our ability to resolve this. These are created naturally in your flow field. Yeah. And it turns out that it's not represented, and they get aliased, and that's down here. So this gets basically aliased then onto the resolved scale, and that when you now look, the two together become a hook. And that's a sign in your kinetic energy spectra that things go wrong. Yeah? That's the accumulation of energy at the smallest scales. And that's what the diffusion needs to battle. Yeah, that's what we are after. We are after these artificial processes here at the grid scale, where we are seeing accumulation of energy, and that will blow up. I have some examples. That will blow up on us. Yeah. So after, and Pete mentioned that there are these initial disturbances that just grow and grow and grow, and at some point it's gone. Yeah. So what he also showed. So that's what diffusion is doing, and there are these various ways of doing diffusion, and I listed just the categories. Oops, here. There is explicitly added diffusion, so we are explicitly doing something to the equation of motion that I showed yesterday. Another term on top, that is then the diffusive term. Or we can do some filtering, and this is a little bit of a different flavor. Today, I don't hit on that, but the book chapter will, if you take a look. And then we also can actually use implicit numerical diffusion that's already present in our choice of numerical scheme. And that's very different for finite volume method versus spectral element method. And this is very, dependent. Yeah? So if you really, again, want to say dive deep, I want to also motivate this with some, proofs from the literature that diffusion matters. And this I'm grabbing here from GFDL. So these are NOAA publications, two different NOAA publications here, one by Zhao and, three, Gao and Lucas Harris. And what we are seeing is, let me maybe start here with this diagram. We are seeing actually a simulation of a Hurricane Imar, and this is a timeline down here over hours. And this is the max velocity of that hurricane. And then they simulated observations in black, and then we have a monotonic scheme in this. And this is a FE3 model, and we have a positive definite, and these are two different jargons. Yeah, there are different diffusion properties in those choices, and we can switch them on actually via name list. And you see now very clearly that the positive definite is kind of okay looking this is less diffusive. It's kind of matching the observations really well. And the monotonic one, which is really adding more diffusion, monotonicity constraints, I'll show you in a minute, is actually suppressing this hurricane big time. So this is really decisive. This is also, this is now the minimum pressure. This is surface pressure. So that's kind of, basically goes hand in hand here. We have another motivation here, and this again comes from Zhao. We are, I guess up here, you see some sensitivity to a parameter, E0. Let's not worry about what it really is. It's a cumulus parameter in the physics. And we are now looking at an annual count of TCs and hurricanes. TCs, tropical cyclones, hurricanes are these major tropical cyclones. And this is a count, annual count, and just by variation, you see the variation in the cumulus parameter, you get very different counts. So this is kind of the essence here. And if you are doing, and this is physics, and if we go into the dynamics, and in the dynamics we have a switch in FE3, which is called divergence damping. It's a diffusion process. And now you see also a parameter down here. This is a value that you put into the name list for the diffusion, for the divergence damping, versus annual count. And yes, again, we have very different counts, and we only changed one parameter in the dynamical core and nothing else. A very scary situation. We are reliable. We trust. Maybe we even think the die core is really good, and the physics screw up. No, not necessarily. So we are very sensitive, and the composition between physics and dynamics is decisive as well. We have this huge dependency here on divergence damping. That's I don't know whether we fully understand, actually. There are some arguments that actually higher values are better. You see higher values give you more count because you actually get rid of more noise, and more noise gets actually lets the system organize better for the hurricane thunderstorms and so, So you take away the noise, but that helps actually the convection. So that's to be debated, Okay, all right. So here are the jargons or the keywords that I could talk about, but I only highlighted the ones in red that I will touch upon, and I probably don't even have time to do all this. So I'm going after explicitly added diffusion, and there could be horizontal diffusion or hyperdiffusion. That's in MPAS and SE. Horizontal divergence damping. That's in FE3. We have in FE3 vorticity damping. I leave out external mode damping available in FE3, and then Rayleigh friction or other sponge layer mechanisms near the model top. That's in all models, but in various forms. Right. Next item is numerical diffusion or implicit numerical diffusion, and here we are hitting after the order of accuracy, and also we are looking at monotonicity constraints and flux limiters, and this kind of goes back a little bit to Owen's lectures on finite volume methods, and I kind of maybe illustrate how that works. And these are also available switch-on options, especially in FE3. We have a variety of monotonicity constraints for the finite volume scheme that we can switch or test out. Order of accuracy also available in FE3. We don't have those, a little bit in MPAS actually, not so much in SE. Okay, and I don't think I can really talk about any filters, and there's another category I should talk about, which is fixers, but if the mass isn't conserved, but you want it to be conserved, and you do it after the fact, So you fix it after a time step, you bring back the missing energy or the mass into the system via a fixer. It's not physical, it's just a fixer, but I will not talk about that. All right. Okay, and here's how it looks. So we are thinking now about the equation of motion in a very schematic way. So here we have the time derivative, and we know the time will change with the dynamical core. And we would consider this to be vanilla dynamical core without diffusion, although implicit diffusion would be in it theoretically. Another thing that changes the time of the variable, your forecast variable is physics. Cloud physics, turbulence and so. But what we talk about here is this additional term that we are now separating out as additional diffusion to make things stable. So this is the one. And we are, as a teaser image, I thought I grabbed something from DCMIP-2008, for those who had been there, maybe they'll remember, where we had actually, this is really just advection. So this is a transport of a feature, and that feature is this feature. So this is, we dreamed up the slotted cylinder. It's 3D though. Here we see a cross section in the vertical, here with the latitude, and we transported that with prescribed known velocities around the sphere. And the initial condition, which is this, should have been the reference or is the reference solution. So we have an analytic solution. Advection, as Peter mentioned, shouldn't actually do anything to the flow field. This was with prescribed constant velocities. Yeah? So we actually knew that this is the solution. And these models, we see some of the acronyms here, gave various solutions after we transported it around the sphere. I want to highlight a couple of things you should watch out for also in your own simulations. You want to watch out for noise. Home, for example, this is nothing but this actual spectral element, dynamical core. Want to watch out for noise. These are the ripples. Yeah, this can be battled with diffusion. You also see implicit diffusion. For example, here the Eulerian spectral. This is from NCAR. Eulerian spectral model has yellow colors. There's no yellow here. Yeah, so we are now diffusing out. When you see this color, we are diffusing out actually the initial state, big time. Some models, though, have overshoots, and some have more than one. So the maximum was 1, but now some models even create values more than 1, and this is actually overshoots. This is also a consequence of numerical schemes. That's not good. Yeah, it's not desirable, but that can happen. That's even true, I think, in home here. We see overshoots and in other models. So yeah, and then you see real clear differences between the shapes. So this was a NASA model. This was a really good one in comparison to other models that were smearing out or even losing symmetry. I think there was one model that lost a lot of symmetry. Icon, no, not too bad though, actually. Those are the things you want to watch out for, and diffusion plays a big role here. Yeah. Okay, another example. This is also from DCMIP-2008. Here we used a mountain, which you don't see here, but the mountain is a little bit different than our mountain. It was a very benign flow field, not as aggressive as our mountains, test case 1. It's basically a flow, it's basically a shallow water test case actually, and the mountain generated raspberry waves, and this is now shown here by, this is now the zonal wind field, 700 hectopascals, so we see some waves. The mountain sits actually here, and this was after 25 days, so we have nice, kind of wave trains actually, which when we went to the Eulerian spectral model looked like that. Yeah? And this was a clear sign of underdiffusion. So the pattern is okay, but it's really wiggle, there are lots of wiggles on top. When we crank up the diffusion, we get basically that solution. So yeah, this is where you, again, kind of look for your battle, yeah. Okay, and this is way too much information, but I still wanted to put it up because I want to just display how complex this is. And I really picked everything I know about FE3 and the diffusion FE3, everything I know about the diffusion in MPAS, and maybe I just go, and everything I know about the diffusion in SE, just maybe as a heads up, diffusion in SE is super easy. Yeah? It's actually almost nothing. You have very few turning knobs. And maybe, just point up first, you have really, you have a sponge layer. Well, I guess sponge layer is my second item. You have a fourth order hyperdiffusion. I'll show you in a minute what that is. And that's it. There are various coefficients that you can use. So it's actually doable to do a very different diffusion coefficient for temperature versus pressure or versus some. Yeah, you have a couple of choices. Yeah, the diffusion coefficient might be different, but not the process. Yeah. And then we have in the sponge layer mechanism, we have near the model top, we have second order horizontal Laplacian diffusion. So it's higher, it's more aggressive diffusion. Yeah, fourth order is less aggressive, second order more aggressive. And in some versions, and don't think in our version, at WCAM, there's a version here, high altitude version. There's also Rayleigh friction. I don't think we have that at our disposal here. All right, and then we have, in the advection scheme, we have limiter options, and this is something just for the advection scheme where we are, for example, with monotone, maybe you see the words here, monotone is where you don't allow overshoots and undershoots, yeah, that's monotone. So you try just to keep the data in your range of your initial data. And that's a limit. This is actually the default, but we don't need to do this. We could do sign preserving. This is basically, we allow overshoots, but we don't want undershoots under 0. Negative moisture is really not a good idea, yeah, when you go into the physics. So, but that is an option which is less diffusive. So sign preserving, or you say none, and see what you get, yeah? Good luck, yeah? So it could blow up on you in physics. There is also a hidden diffusion option in the vertical remap algorithm. Remember that, who talked about that? Owen, did you talk? Oh, no. No, okay, no, if somebody talked about it. Peter. Oh, you talked about vertical remaps, right. That actually is, you can do it via, you could do linear remap, bilinear, or whatever, quadratic. There are some options. They're actually better than that. They're, kind of cubic spline or so interpolations. And that is diffusive, yeah? The interpolation is diffusive, so whatever you pick here will have some, and there's a nameless parameter, which I highlight here, where you can actually switch an algorithm out, yeah? But let me go back, and I don't want to really explain all the parameters to you, but I did make an effort, especially with FE3, not with MPass, but we see MPass later, to give you the keywords. Yeah, if you see this in the name list, these are kind of the mechanisms. And I want to hit on divergence damping. I want to hit a little bit on vorticity damping, sponge layer diffusion. There's Rayleigh friction built in, and enhanced divergence damping. There's a Smagorinsky-like second-order divergence damping. You will see what that is. We have another filter. This is actually considered a filter for the sponge layer, but you can drag that down to the surface if you want. It's a filter in the vertical. 2 delta Z waves will be filtered out. That is very decisive, I think, for test case 1 because of our instability. This works on Richardson numbers, yeah, so instability actually. We have something for external mode damping. I don't talk about that. We have implicit diffusion, many options of implicit diffusion. This is the accuracy or the monotonicity constraints, I should say, of the advection scheme. We also have implicit diffusion, the vertical remap, also many options, and we have frictional heating. Again, this is nothing I talk about, but let's say it's super complex, and MPass is also very complex. Yeah, so we have now 3D divergence damping. Instead of 2D divergence damping, we have sponge layer diffusion, different kind though. We are also in the W velocity, which isn't present in the hydrostatic version, at least, of FE3. We have hyperdiffusion, fourth order hyperdiffusion that's used as a background diffusion. On top, we have optional, we have 2-order Laplacian diffusion in various ways. This 2-order Laplacian diffusion is actually there for test cases like ours, which we are not switching it on right now, but you could give it a try. We have 2nd-order Smagorinsky diffusion on top of 4th-order hyperdiffusion, and we have choices here in the accuracy of the advection scheme. Here you kind of see some of the choices. These are nameless options. We have an off-centering parameter, and we have, for the advection, we have positive, definite, and monotonic constraints. Again, this is kind of a lot. Yeah? So let's see how far we get. And this is really easy going, actually. Right? Okay. There are so many things that I can't talk about, so I thought I'd put up the list, things I know where you get more information, starting with the name list option documentation, and unfortunately MPass isn't mentioned, so this is just going after SE and FE3. This is from the community atmosphere model. We have a paper by Peter Lortzen, who is a little bit explaining the SE diffusion mechanism. And then I point you to the user's guide, the MPass user's guide. This is online guide. And for FE3, 2 documents, online documents, the second a little bit out of date, which is actually the explanation of name list. There is very little literature on FE3. Yeah. So these are kind of good, maybe resources. All right, let's kind of understand what diffusion is. Really quickly, this is hyperdiffusion. So at temperature, as an example, hyper means that our Q might not be just 1, it could be 2 or 3 or 4. Yeah, this is hyper. So if it's 1, we have, oh no, even if it's, no, 1 is Laplacian diffusion. Yeah, this is a gradient operator. So if it's 1, it's Laplacian diffusion. If it's 2, it's 4th order hyperdiffusion. And you also see there's a little bit of plus minus business actually going on with that. So you do need that plus minus business. It's, of course, already in the model. Yeah. So this is the essence of hyperdiffusion and Laplacian diffusion. And there is this coefficient here, which has dimensions, and it depends, it's scale sensitive. So I'm pulling this just to give you a little bit of an idea. Here is, well, this is 4th order hyperdiffusion coefficient for various resolutions. You see a couple of the grid distances. This is for Eulerian spectral model, but I just want to note that this scales with factors of 10. Yeah? As you go down, basically as you go down in resolution, you go down in diffusion. Yeah, otherwise you wipe out your new information with diffusion. Yeah, so you want to actually scale diffusion. SE, unfortunately, I don't know, but SE has in the name list has dimensional diffusion coefficients. You need to know the order of those dimensional coefficients. And it's very tricky to do this right for reduced Earth because our reduced Earth puts in another scaling factor. Yeah, so we can talk to your mentor if you want to play with diffusion coefficient in SE. You need to watch out in test case 2 and 3 for that scaling factor for the reduced Earth. Otherwise, it's blowing up on you. Okay, so that's kind of the essence here. Also, if you want to note or have more information, this is how diffusion coefficients are defined in spectral models, and they actually are not random. So this is the N0 will be your smallest resolved wave number, like 85 in my example, I think this is even 85 here in my example. So let's put 85 wave numbers for spectral model, and A is the radius of the Earth, and this is your time scale for diffusion. Let's say a day, an hour. Yeah, here you see some typical time scales, couple of hours. That's a typical time scale you pick for your diffusive process, and it means that a wave will actually be diminished by the factor of E during that time. And the waves work, and you see a little bit of that sensitivity here, hyperdiffusion. So I'm going higher in order, and this is a so-called response function over wave number. So as you go to high wave number, small scale, you see that the second order is actually really aggressive. The black one, it's working really aggressively even on resolved wave numbers. Diffusion should really only work on the smallest wave number. And second order doesn't do that. Second order is really broad. That's where it's aggressive. But as you go to the higher order, fourth order, and so you actually see that you are more and more focused with your diffusion, meaning you deviate from one, at those higher wave numbers. It's a little bit unclear, or I make a suggestion here how to go after the estimation of the diffusion coefficient here in grid point models, but this could kind of serve here as a guideline. Yeah, so the dx would be the spacing. I know cubed spheres have different spacing x and y, so it's not 100%. Yeah, but this could be a guideline. Okay. Okay, and then also let me show you, this is hyperdiffusion. I start with hyperdiffusion to just show you what the effect is. And I was really aggressive here. This is a model, the Eulerian model, where I used the standard, this would be the standard coefficient of hyperdiffusion with a time scale of about 9 hours. And then I go and I go 10 times higher, and the time scale for the smallest waves is now under an hour, the reduction by factor of E. And you clearly see this about clinical wave test case. You clearly see, for example, here in the temperature field, as is after a couple of days, a really sharp, nice temperature gradient here in the normal one, and this is diffused out in our high diffusion one. Yeah, so this is really the essence of diffusion. I want to say, though, there are good things about it as well. This is not good, but here you see my normal one was very much noisy. And with my high diffusion, I got rid of noise, but I got also rid of my signal, and therefore not good. Yeah, so that's probably not the way to go. By now, this model is legacy, and we are not using it any longer. Yeah, so but those were the options for those hyperdiffusion models. And SE, MPAS have those options. Yeah. All right, I want to move on. It's really quick here. Horizontal divergence damping. So that's actually something in FE3 only. MPAS has 3-dimensional divergence, but horizontal divergence that is denoted here by D. That's D. You compute the horizontal divergence. And here is the essence of divergence damping. It very much looks like so you have a coefficient, that's actually this one, and a gradient with some higher order, Q, doesn't need to be 1, operating on the V field. This is a 2D velocity field, U and V, and then plus minus business. And here's kind of how it works. So you actually append a gradient of a coefficient times D to the horizontal momentum equation. Then you, kind of think about application of a divergence operation. Yeah, you create the divergence here, which then creates a Laplacian on that side. And basically what you get with this is the diffusion, the time tendency of divergence gets a Laplacian diffusion, and that's what it is. Yeah, so it's actually now getting a second order Laplacian diffusion on divergence. And 2D divergence grams gravity waves, 3D divergence and MPAS damps sound waves. It's a very different beast, yeah, these two. And the choice here of that C coefficient actually is not random. It actually needs to be stable. It has stability constraints. That's actually really, there's a very narrow band, and Tim knows all about it, and we can point you. I think we have actually recommendations on the webpage. For FV3. All right, here's the effect. I just want to, this is extreme, yeah? So if I really have a super high divergence damping mechanism on, I'm getting, this is a test case also from DCMIP back in 2008 and also in, I think, 2012. You see a gravity wave propagating. This is at the equator. This is just a temperature variation, a temperature perturbation. So the gravity wave was starting here in the middle, and there we have two wave fronts. And this is very much diffused. As you see, this is with very high diffusion. And as we then go without that divergence damping, we get that signal. This is in, this wasn't FV3, but this applies to FV3. This was in FV Laplon, yeah? But it's the same mechanism. And that was then really a clear signal that the divergence damping, the diffusion took out the signal. So we did this also with all other models. This was during DCMIP 2008, and just a couple of snapshots to tune you in here. So, if you did it here with the Camolarian model, no explicit diffusion, we got very, very sharp fronts of this gravity wave. Well, when we turned on, this is technically default fourth order hyperdiffusion, smeared out, yeah? So you lose actually the sharp edge, and you lose actually the magnitude. And here is again FV or FV3, think about that, no divergence damping, what I just showed. And this was CAM-SE with fourth order hyperdiffusion. Yeah, so this is actually pretty nice actually here in SE. So this is really kind of a consequence of that choice. Another consequence, and there I'm just pointing out, it's not an option for us technically to run FV3 without divergence damping. So you can maybe get by in some very idealized test cases, but as you go even to a baroclinic wave, every FV3 falls into a mode which you can't recognize. Yeah. So here we have now, this is really just a normal run FV3, here with second order divergence damping, and then just switch it off. You can do it via namelist, and we didn't blow up yet, yeah, but probably soon. Yeah. So here you can't even recognize a baroclinic wave, well, a little bit, but this is so polluted from noise that it's not a solution. Yeah. So it's actually a needed feature. It's not even a choice for us, but we could go higher order than second order, and that's basically what I want to show you next. Actually, no, I think I skipped over one. Oops, no. I think I'm too quick here. Let me go back. All right. Okay, so yeah, and I showed you the kinetic energy just a minute ago as a schematic, but here is now a measurement of kinetic energy. So again, you want to think about this here in scales, circle wave number, the higher you go, the smaller the scale, and here's the kinetic energy. This is called the kinetic energy spectrum, and this is from a baroclinic wave at 700 hectopascal. So you see a lot of zigzaggy, that's okay. And then down here, you really want to just look here, and you see now, you see the FV, FV3, no divergence damping. This is exactly the noise you saw on my previous slide. Yeah. So this is now picking up the energy at the small scale, is now picked up here in that analysis, and that's not the case as you go to other models or if you switch on divergence damping. Yeah. So that's kind of the essence of that. We have, and this is an interesting feature of FV, we have FV3. We have a lot of options for the divergence damping, and here I want to just highlight them. So there are second order divergence damping, fourth order, sixth order, eighth order, and yeah, I have even two examples of eighth order. And again, now it's a little smoother looking, my kinetic energy. This is from an aquaplanet study where you run the model without land. But you want to really, again, point to tails. This is also smoothed over many time steps. You do see now the diffusion effects as you go, for example, to eighth order. Eighth order is less diffusive, less aggressive, higher order. You clearly see that eighth order gets you, more energy here at the grid scale. You also see a little bit of that upward slope already. Yeah. So that's actually an indication that eighth order may be not good. Yeah. You don't want upward, yeah, because you want downward. But you maybe need to think about how steep downward. Yeah, and you will see more examples. Steep downward, not good. Yeah, steep downward is not a good effective resolution. Yeah, ideally you want to be aligned with the reference here. This is the reference how it should look. This is kind of a so-called K-3 line, how it should look. All right. Okay. I have also, this is another kind of teaser. This is all FV3 actually now. This is a baroclinic wave, and I guess on purpose I saturated the color to highlight noise. Yeah? So here we see 850 hectopascal vertical velocity with various settings. We have various settings of divergence. Here, sixth order divergence damping versus eighth order divergence damping. And those eighth order have actually additional diffusion on top, yeah? So it's not actually just that. And you see all kinds of mechanisms. Well, you see also a lot of grid imprinting noise here in some of them, not so much in this one. So yeah, you see basically, and this is really why I encourage you to play with the diffusion. I'm really curious what Scoreline probably will bring. Some of this will blow up on us if we are not even, and I highlight this a little bit here, FV, the NOR3, which is eighth order diffusion, typically blows up on you. If you, or you can prevent it if you have additional Smagorinsky diffusion or other things on top that take. I always say, yeah, you take your medicine, that is the divergence, yeah, and then you take more medicine to battle the side effects of that first medicine. Yeah, so this is basically, if we have eighth order divergence damping, we then switch on other damping to battle the instability actually that's not taken care of by divergence damping. All right, here's actually the blow up, or it's close to doing that. This is with eighth order divergence damping. This would be how you also detect it in verticals. This is now from the baroclinic wave vertical cross section latitude. This is how it should look. Now this is actually the meridional wind field. With sixth order divergence damping, and here it's eighth order divergence damping, and now we see checkerboarding. Checkerboarding bad, yeah. So checkerboarding basically gets you to your blow up really soon, yeah. This is 2 delta X, 2 delta Z, yeah. So this is not good, and diffusion takes care of 2 delta, 3 delta, 4 delta, hopefully not 10 delta, yeah. So that's where it shouldn't actually work. All right, okay, so. That's that. And I think last but not least, for explicit diffusion, I have vorticity damping. And that's only available in FV3. And I highlight that this is from Tim's slides, actually, that I grabbed from PDEs. But here's how this works now for FV3. We have the divergence damping up here, just maybe written a little bit differently. And then we have another one, which is the vorticity damping. And that's the essence of that. And it's the same mechanism. So we have Laplacian with higher order possible, working now on vorticity. And this is really how it ends up. So it's ending up as a forecast equation for the vorticity being damped by a second order, fourth order, or eighth order, or whatever you have. I don't think eighth order is not available, I believe, no? Sixth order, I believe. And here is kind of how this works. I don't have actual simulations that I show you. I just want to highlight that these coefficients, these are diffusion coefficients, they are nameless options, and they have these narrow stability ranges. So, kind of take a look at the documentation we provide. If you want to play, this can blow up on you if you overdo it. Yeah, so it's then blowing up before you are unstable in the diffusion. Yeah, so that's not what you want. All right. Okay, sponge layer, and then I go to implicit diffusion. Sponge layer is everything you do at the model top, and Dave was hitting on that a little bit. You want to absorb upward traveling waves, very hard to find absorbing mechanisms. Gravity waves may be easies, but we have all kinds of waves that travel upward, and they get reflected, and once they hit the model top, they often come down on you, and that is interfering with the solution. And that's true for the DCMIP test cases. We have the Rayleigh friction on in all of them. No, actually, yeah, no. The Scoreline is a little mixed bag. We have sponge, but not all Rayleigh friction. But let me kind of walk you through it. So this is Rayleigh friction. This is just shown for the U velocity, but you will also apply to V velocity or maybe even W. And it's basically your forecast is augmented by a tau, which is 1 over a time scale. Time scale would be a day, 2 days, 5 days, whatever you want, 1 over. And then that multiplies U minus U bar. And that U bar may be 0. So if you set that U bar, that is a background U. In our test cases, test 2, it's actually 10 meters per second with the solid binary rotation. So our U bar may be not 0, but it could be 0. If you have that, you see what it does. It's dragging the U to 0. Now, assume this is 0 over time. So you would always try to drag it down to 0. And that's basically Rayleigh friction. And here you see now the sponge layer, the second order Laplacian diffusion. This is just second order Laplacian applied to U. Technically, it's incorrect actually the way I'm writing it because U and V you would need a spherical version, well, I guess I'm not exposing this even, how you define this Laplacian. You need to be a little careful. The typical way people, SE even applies to diffusion is not on U and V, but on vorticity and divergence, which are scalars. And this is basically what scalars will do, yeah? So it's a little bit tricky to do it with vectors, but this is the essence of it, yeah. And what does it do? So this is in the book, but here I just kind of ran a Hertz-Rarus experiment. So this is a very idealized climate simulation. And the only thing that I did, and this was, again, this legacy DICOR, the only thing I varied was sponge layer diffusion. For example, second order sponge layer diffusion, no sponge layer diffusion, really strong Rayleigh friction, not so strong Rayleigh friction. Strong means I'm just tweaking the time scale of my Rayleigh friction. And and apply it, above 1, here the Rayleigh friction, and you clearly see the weak Rayleigh friction is very different than a strong Rayleigh friction, yeah? So here it's taking out my complete signal. This is a zonal wind here at the time mean, zonal wind. So this is maybe overdoing it. And it's, an art to some degree. No sponge layer gets me to really high values of velocity, not blowing up on me, but high values, yeah? So it's really different. So you basically, and I think other people mentioned that, you cannot really trust anything in the sponge layer, yeah? Don't try to do any science in the sponge layer, and don't even try maybe to do science just below the sponge layer, yeah? So maybe between 1 and 10. Sponge layer also radiates downward. So it's affected, yeah, because you do affect the whole flow field, and it's seen by even flow that's not in the sponge layer. So you want to be away from the sponge layer when you interpret things physically. Yeah. Okay, all right. I want to switch topic, going from explicit diffusion to implicit numerical diffusion. Right, and this is kind of where we are hitting on the order of accuracy, for example, first order, second order, third order, those orders of accuracy, which are present in the spatial and the temporal discretization. Here I'm referring to it in the spatial discretization. We have in SE, we have technically fourth order accuracy. In FE, we have third order accuracy, although this is technically in very idealized cases, so it's not necessarily true here in our 2D or 3D environments. The higher the order, the better. Yeah, that's kind of the rule. The higher the order, the less diffusive. Yeah. And we can then apply monotonicity constraints to finite volume methods. There's also implicit numerical diffusion in off-centering, and I don't talk about that today in semi-implicit or semi-Lagrange methods. You can play a couple of tricks. So I only talk about out of accuracy and monotonicity. And here is kind of a list that's available in FE, FE3, first order, second order, third order. And here are kind of the names of the people. Bram van Leer, and PPM was developed by Philip Colella. And so these are the words, the keywords of the algorithms, and they can be augmented with monotonicity constraints or positive definite constraints. So just to illustrate that, this is basically what Owen showed you. So this is, let's think about a finite volume method, and this is the easiest you can do. We have these grid points, and we think about constant subgrid distribution in all cells. This is the easiest you can do, would get you a first order method. Yeah, first order very diffusive. Okay, maybe don't want to do it. Second order would be if you would try to fit a linear subgrid distribution in your models informed by neighbors. Yeah, so you will look at neighbors and you would do a slope, and even you could do, this is second order accurate. And then if you go higher order, like parabolas, this is a piecewise parabolic method. So basically it just builds better subgrid distributions. You basically get, they can be discontinuous. There's stepwise parabolas in each of the cells. And what I mean by diffusion and monotonicity constraint is the following. So if this is now this is a linear, this is just really an example illustration. So let's assume that my reconstruction of the subgrid distribution got me my blue line. And now we are seeing a problem because my blue line down here at the edge is really smaller than my support next to my neighbor. There's no physical support for that. Yeah, there's no reason that I should assume that this value should undershoot the value to its left. And that's not what you want. And that's what monotonicity constraints are doing. They are looking at those situations after you build subgrid distributions. They look, is this a possibility that you overshoot or undershoot your neighbor? And if yes, limit. And that's the limiter, and monotonicity constraints is just a limiter, and this is basically what the limiter does. It then flattens the subgrid distribution in a way that avoids the overshoot and undershoot at the edge. And that's that's a monotonicity constraint or limiter. It is diffusive, because we have a less sharp profile. But it's good for monotonicity. It gets rid of wiggles, for example. So that's really the essence of monotonicity constraints or limiters. And here you see the essence of order of accuracy. So order of accuracy, this is a Bartlett wave, first order, no Bartlett wave. So 100% diffused. As I'm going to second order van Leer with the linear subgrid distribution, I'm getting this. And then third order, almost alike, but a little bit sharper, a little bit better resolved. This is here the temperature at 850, kind of really nice sharp temperature front, a little bit broken here with the diffusion that's in this second order scheme. So this is kind of what you can look at in terms of order of accuracy in FV. And it's also visible in the kinetic energy spectrum here. I've shown it again, first order in red, second order in blue, and then third order with two different monotonicity constraints. And you see even the difference now here with PPM scheme here in green and in yellow. They are both third order, but they have the different constraints, the monotonicity, and it does show up in my damping. I don't have a hook, so I'm diffused, yes, but I'm super diffused in first order. You don't want to be there. I'm actually also somewhat more diffused in second order. Okay, so that's where you look for. And these are the kind of, when you look at name list options for FV3, here you have these cryptic options, and these are the cryptic parameters in the name list. In CAM, you also actually append an FV3 underscore before. So the name is this with an FV3 as a prefix. So this is actually from a NOAA I think tutorial notes from Lucas Harris here that I'm showing. But these are kind of some options you have. These options, these magic numbers give you various. 5 is the least diffusive, and that blows up probably if you're not careful. And then we have others that are more diffusive, and you could give it a try. When I say give it a try, here's an example of various ones. So here we have H-ORT 5, 6, 8, and 10. This is the magic number. 5 least diffusive, and you see least diffusive is a Bartlett wave. Again, here with, you see H-ORT 5, 6, 8, 10. Bartlett wave with, this is actually from Owen's test case with the mountain. We see surface pressure, at some point. And here it's a little easier to see maybe differences in the minimum surface pressure over time. And you see clearly that 5 gives us the most intensification. 5, the least diffusive one, basically means that it's maybe less clear to see here in the visuals, but our most developed low pressure systems here in purple are lower. They have lower minimum pressure values. And as you then crank up diffusion, you actually, it's sizable. It's about, I think, even 10 hectopascal difference after 10 days of 5 days of forecast. 10 hectopascal difference in your forecast. So it's a lot of difference just due to the implicit numerical diffusion due to limiters. It's all PPM, but it's limiters now that do this job. This is also, and if you put it into context with other models, for example, spectral element and MPAS, in their least diffusive configurations, we are actually matching to, when you kind of see the green here and the yellow or the orange, they are overlapping actually FV in the least diffusive option, and then the other FV3 options become more diffusive. So it's again an indication, I guess, that least diffusive actually, maybe it's at least met by other models. So we don't have a reference solution, but that is an indication. Maybe that's a good one to use. All right, and I think one more on that, and then I have 1 or 2 more things to tell you. Here is also proof of the pudding, I guess, that may point you to it. This is 2 different, these are FV3, coarse resolution. This is 100 kilometer resolution, C96, and then here 50 kilometer resolution. And here I'm switching, the 2 are just, less diffusive, more diffusive. And what I really was surprised by when you basically now, again, look at, let me point you to it here, look at the minimum surface pressure evolution over 5 days. Well, of course, H-ORT 5 least diffusive, that's really sticking out as, really intensifying the most here in the high resolution. But as you then switch the high resolution to more diffusive, and that gets you to the black line, it's now matching the red line, and the red line is actually 100 kilometer least diffusive. So all this nice, all the nice properties of high resolution goes down the drain with more diffusion, and I'm now matching 100-kilometer resolution. Yeah? I paid all this extra expense, 8 times more compute to get nothing. Yeah? So that's really something you need to consider when you make decisions about diffusion. These signals also pop up actually in precipitation, which I was surprised to see. Precipitation, least diffusive, actually most precipitation, and that's maybe explained by more rigorous updrafts, which this is a moist version of this test case. More updrafts, more precipitation, and as I suppress the energy a little bit, I'm getting suppressed precipitation. Okay, okay, one more, and then I also have MPAS information for you, which I left out a little bit so far. Yeah, so you see the numerical diffusion in the limiters. Again, this is all ppm, but with least diffusive and more diffusive. You see it also in aquaplanet very clearly here. Separation of the energy, the kinetic energy here at the finer scales. And if I put that into context, and context means this is, again, aquaplanet, same physics package, now with MPAS, SE, and the 2 different options that I just showed. And then we see a really intriguing, maybe even a comparison here between the diffusive aspects of MPAS and SE versus the diffusive aspects of FE3. I was actually surprised to see that MPAS, both MPAS and SE, seem to be more diffusive here at the grid scale. They have, you kind of see that they are they do a deep dive here at some point versus FE3 being kind of more along the reference line in its least diffusive options. Although again, you might want to double check whether you can run with this or, basically whether you are stable with that. Okay. All right. Okay, I should wrap up. So I have some slides that are more optional. Maybe I spend a few more minutes because I also want to leave time for questions. But this is something I maybe should touch upon because Smagorinsky diffusion is also actually something in FE3 and MPAS. Although I should say we call it Smagorinsky in FE3 and it's really not. Yeah. So I want to just maybe, this is Smagorinsky for GFDL. If you haven't seen him in a photo, he invented, I'll show you in our next slide, but he came up with a diffusion scheme that takes advantage of kinematics. And for those who haven't taken a fluids class in recent years, this is nothing but divergence versus relative vorticity. You see some of the definitions: horizontal divergence, vorticity, and there are 2 more. This is stretching deformation and shearing deformation, and they come into play in the Smagorinsky diffusion concept. Yeah, so these guys are new. Yeah, so these are the 2 combinations that you can do with du and dv. Yeah, in x and y. Okay, so what divergence damping is, Smagorinsky is all about. Is this. So this is now a forecast variable, and now we are looking, it looks like Laplacian diffusion. Yeah, so we have a coefficient, we have a double gradient working on our variable, and that coefficient is the trick because that coefficient is not a constant, but it's now a flow-dependent quantity, and that's how it looks. This is a flow-dependent quantity. There is a nameless option in MPAS. This is set default to something. There is something in there. There's the average grid spacing, which would be in MPAS just your grid spacing. I don't know, whatever we have in the name list. Oh, that's actually a good point. That would need to be scaled maybe with the X factor. Okay. The name list maybe has actually the wrong information. Yeah, the name list has 120 kilometers or 60 kilometers. That maybe needs to be looked at. And then we have the stretching deformation definition, and we have the shearing deformation squared, and then taking the square root, and that gives a flow-dependent diffusion coefficient that should really only come into play when you are in these situations. When when you are in the situations of a lot of, a lot of shear or a lot of deformation, shearing or stretching deformation. So it really is specific to get rid of that. Yeah, so that's the trick. Otherwise, this would not really. The coefficient is more like 0. Yeah, okay. And unfortunately, FE3 calls this Smagorinsky diffusion, but it's not. Yeah, so the implementation of what's called Smagorinsky-like diffusion is this. This is what FE3 does. So it's looking like it, but the diffusion coefficient is determined by this is a nameless parameter, it's a time step, and then it's not using shearing, shearing and stretching deformation, or shearing deformation and stretching
it's using divergence and vorticity. Yeah? It is flow dependent, but it's not the same as Smagorinsky envisioned. Yeah? So I just want to point this out. If you play with that, this needs to be understood. Yeah? It's that we are not apple to apple when we do Smagorinsky. And I want to just maybe before I show you MPass and then I close, I want to point out that this can help. So here I had a situation where I had a very aggressive, non-diffusive, H-ORT 5, yeah, so least diffusive option in FV3. Things started to bubble up, and a couple of day later it blew up on me, and I could actually avoid the blow up. This is the clinic wave from Paul Ulrich, DCMIP-2016 basically, and here with Smagorinsky diffusion that you don't see, but this is now on top, it actually was okay. Yeah, so Smagorinsky diffusion took out my instability that developed with my least diffusive option in FV3. All right. Let me just close with, I don't think I can touch upon that. Maybe take a look. These slides are offered. We post them in the FV3 group. We can also talk about it. This is the sponge layer diffusion based on Richardson number, but I don't have time. And I will just skip to, and this I took from MPass tutorial notes. This is not from my work. I just grabbed a couple of slides from a tutorial that was given a couple of years ago. And you see some of these, I just want to point you at MPass group to some of the parameters you want to look at. So for example, you have those choices. You can do 2D Smagorinsky. This is on top of background fourth order hyperdiffusion, which is always on typically. And then you have, for example, you have a Smagorinsky diffusion coefficient. I'll show you in a minute. I don't think that's actually shown here. We have another one that's toggling between third order and fourth order accuracy in advection, and that's set actually by these guys, and you see a little bit of that explanation more here in my guide, not my guide, but the user's guide for MPass. MPass has, and here now we see the Smagorinsky diffusion coefficient. These are non-dimensional, actually. That's nice because they don't change with resolution. But, and I think I pointed you, let me just double check. I think I pointed you here. No, it's hidden. So you don't know, it's hidden already. It's mingled, this coefficient is mingled into this definition of your diffusion coefficient. So let's not worry about it, yeah? So that's that. And then if I go again to MPass, here is now the coefficient for, this is a coefficient for fourth order background diffusion, that one actually. And then we have, we have the ability even to do more aggressive diffusion. This is hyperdiffusion, but we can do more aggressive diffusion for divergent motions versus rotational motions. That's also true in SE, actually. That's a choice in your name list. And then last but not least, you can, for idealized test cases, which we are, you can also switch on, this is hidden typically, but you can switch on second order Laplacian diffusion if you want. This is super aggressive, but you would need to change your setting to 2D fixed instead of 2D Smagorinsky. Yeah. So these are now the options. You need the prefix MPass underscore in front of these names. All right. Okay, I want to wrap up. So it was a walkthrough, really quick walkthrough to the diffusion options, not everything under the sky, but a lot of things that you might be interested in here at DCMIP. So, we talked about horizontal diffusion or hyperdiffusion, horizontal divergence damping, vorticity damping briefly, Rayleigh friction or sponge layer mechanisms. We talked about the implicit numerical diffusion out of accuracies one in FV, FV3, and also MPass. And we have monotonicity constraints in FV and technically also in SE and MPass for trace advection, trace advection only, but we have a lot of these for FE in terms of advection of the actual forecast variables. We did not talk about filters, which, for example, could be Fourier filters, like polar filters was mentioned, I guess, Dave, for polar effects, that noise in the polar region, in Laplande grids, for example. There are other filters, time filters, which is something that Pete, I guess you didn't talk about time filters, but if you ever do a leapfrog, which Pete touched upon, it will blow up on you after a while. You need the time filter, which is called SLN filter, on top of your leapfrog scheme. Yeah. So these are kind of two delta filters for time, or not just two delta, but filters grid point filters basically. And then, yeah, there could be, other things in your model like tracer mass conservation, total energy conservation, mass conservation, and so on. And if you really want to know it, take a look at the book. Okay, I close here.
On the left.
Okay. What's the advantage of the vorticity and the can you go back a few slides? I want to make sure I get the term right. You have damping, you can damp with U and V components, or you can damp with divergence and vorticity. What is the advantage of doing the vorticity and divergence damping?
Well, it's just divergence damping damps divergence, and vorticity damping damps rotation.
Right, but if you're damping U and V, aren't you going to achieve essentially the same thing?
Right. And that's true. Hyperdiffusion does that. Hyperdiffusion, damps both actually. But here we don't have hyperdiffusion in SE. Yeah, we don't have hyperdiffusion. We only have divergence damping for divergence and vorticity damping. Yes, that's basically now technical part.
Okay.
Okay, Caleb.
This is very interesting, so thanks for the talk. I'm curious what you think, because these schemes are not always particularly physical, what would be the philosophy for like rigorous choice in diffusion scheme? Like, are we just going for like the least amount of damage that makes the simulation stable? Like, what are we looking for here?
Well, it's very complicated because in the end, think about that analogy that I presented, I think yesterday. You think about it as you go to a concert, every instrument needs to play well with each other, and that's the case here. So if you have more damping in your numerics, implicit diffusion, you probably don't want a lot of damping in explicit damping on top. Yeah. So it's not clear. You really need to figure it out for your particular choice of model, what is the right amount of damping, but you want to do the least amount. Yeah. The least amount that stays stable and gets you shock ratings.
Could you explain why the sign limiting preservers in the first half of the talk might lead to instability, and like how do these
instability wiggles noise.
Yeah, okay.
It does not necessarily blow up at you. It's not actually a given. No, it's just overshoots can happen. If you have only a sign preserving limiter, it will basically make sure, for example, moisture it never be under zero, but it lets you overshoot. It can be more than you had in the first place.
So are those used operationally in any of these so that ensure no negative moisture?
Yeah, they are less diffusive, yeah. I think even GFDL less. It's a choice, I think SE has positive definite, which is a sign preserving one. That's actually, you can, I don't think we have an advection test case this time around. Yeah, we had advection test cases in other DCMIPs where we see it clearly, and it was maybe a little hard to see actually in our test cases. These choices. Yeah. Or, I don't know. Yeah, go ahead.
In addition to kinetic energy spectra, is there anything else you look at to see if you have?
Well, yeah, I do look at the fields. Yeah, so just surface pressure often tells a story.
I had another question. So sometimes people talk about the inverse energy cascade, especially in 2D turbulence. Do you see any of that? And if so, what is the effect of
hyperviscosity? Are you thinking transition from K-3 to K-5/3? Yeah, this is, that does happen. I'm here with very coarse resolution simulations and 1 degree, which doesn't have that. If you want to see a transition, these slopes that I showed you in the kinetic energy should actually become shallower and this basically denotes 3D turbulence going over 2D turbulence. But that happens at small scales, which I didn't have. So if you have, for example, a model with, 25 kilometer resolution or even finer, you should see that unless your diffusion takes it out.
Okay.
Thanks for the talk. What factors cause FV to require more dissipation?
I didn't get it. Say again, please.
What is the main factor that causes FV to need more diffusion?
What's the mean factor? So
the mean factor.
Yeah, meaning, well.
I guess yes, the grid selection or numeric method.
Or numerical method.
And I wonder if there a relationship between the grid selection and your
I think we heard from Dave
that MPass is only going second order. I guess that's due to the grid selection, no?
Yes.
Okay, so grid selection limits MPass to go higher than third order. The advection can go higher than third order, so some piece of MPass are higher order than second, but overall, the dicore overall, yeah, that is a consequence of our grid selection. Good question. Let's see, you first, and then we go this way. Yeah.
Yeah, thank you for the talk. You said by increasing the diffusivity, we have steeper shape in a kinetic energy spectrum. I was wondering, is that because the small scales are damping, or that's because changing in pi or energy flux spectrum?
The diffusion works more strongly on the smaller scales at the grid scale, 2 delta x, 3 delta, 4 delta, 5 delta, and that's why we see the sharp descent of the slopes. That's where diffusion should act, and it should not act on the big scales, which are kind of towards me. So that's really what you want. That's the consequence. So steep slopes come from the diffusion really being aggressive at small scale. I think we have this. Yeah, go first.
Thank you for the great talk. I was wondering whether it's like a common practice to like turn on implicit diffusion and then adjust explicit diffusion after.
Yeah, you would probably do that. Depends. The spectral element model very undiffusive. Yeah? So there you don't have that option, and you only have the explicit diffusion. But yes, in finite volume MPass, you do have these other knobs. Accuracy knob, not too. MPass is a lot of extra external diffusion, not so much internal. And I'm not even certain that I have a knob in. There's no slope limiter that I know of in MPass actually. Yeah, but that's a strategy. You should take a look. Maybe you have no diffusion needs, actually, no explicit diffusion needs, depending on the diffusivity of your scheme. That's great. I think let's see here, and then Taurus.
So you kind of mentioned how, in theory, we'd want to scale, diffuse the smallest scales the most, and that as we increase our order, that will more selectively, select those smaller scales. But you also kind of showed how eighth order isn't always
an improvement. It's under-diffused. Yeah. It's not good enough. Yeah, you're right. It's this dicey balance between too much and too little. Yes. And it's needed for stability. Charles.
So I'm thinking about it in atmospheric models, another place where diffusion comes in the vertical, the boundary layer, the turbulence parameterization often implemented as second order diffusion with some physical meaning behind the diffusion coefficient. But now that we're getting down to models that are approaching almost three-dimensional flow scales, is there any talk in the dicore community about starting to think about unifying vertical and horizontal diffusion?
Good question. I don't think so. Even in MPass has, I guess, a 3D concept with divergence damping. Divergence is not a 2D divergence, but a 3D divergence, but it damps sound waves. It's a very different beast in a non-hydrostatic model that's not present in hydrostatic configurations. I haven't seen any 3D Laplacian diffusion that also would then work in the vertical. I think the switch-on options in MPass, that the idealized switch-on options is a chance it is implemented in the second order as 3D diffusion, because in even former DCMIPs or in former MPass test cases, they needed 3D Laplacian diffusion for their own test cases. There's a chance we have that available because they needed that for their own purpose via the viscosity for the 2D. That's a good point. We should double check whether it's 2D or 3D divergence, Laplacian diffusion. But it's not, I don't think they do 3D, at least I would be surprised in the hyperdiffusion. Yeah, that's a different piece. I didn't talk about vertical diffusion. Vertical diffusion comes in also through physics. There's turbulence schemes that do a lot of mixing in the vertical. The sponge layer that I skipped over for the FE3 group, that is a vertical diffusion, actually, kind of getting rid of instability in the vertical and the Weisler frequencies. Yeah, that's another beast on top. That's typically second order diffusion. Maybe
one more.
Two more, yeah. Okay, maybe, and when I talk to you later, yeah.
Thank you, very good talk. And my question is about transport. I have mentioned, and I have seen that the transport profile and the diffusion profile are maybe very similar, and I can see a lot of parameters can control these two profiles. And do you think is there any relationship between the two profiles, between transport and the diffusion?
It depends.
As we, for example, know in SE, the transport scheme is a similar branch scheme, and that's not true for the actual spectral element dichord. So we often have even different choices in algorithm for transport. FE3 is a little bit clearer. FE3 has FE3 transport. FE3 is the closest where you could have an analogy. So if your transport is very diffusive, yes, your model should be very diffusive. It's also a little bit more separated in MPAS. MPAS has kind of some specialties, I guess, for pure tracer transport. But it's a good thing to start maybe in transport. Yeah.
Okay, let's
All right.
thank Christiana.
Oh, yeah, thanks for that.
So two things. One, the blade file system is down. So we're frantically trying to figure out what to do. So please stay tuned. So I think we'll still meet in the library, but we'll see what we can do. And number two, time to prepare.
Right. I would recommend, I don't know whether you want your name tag in the photo. If not, you can put it back here.